Good morning.
Good morning.
So it must be very early morning for you. Thanks for coming.
It is, yes, it is 5:45 here.
So we miss you. We are missing you.
Okay.
Your physical presence, but not so. You are not here.
So we got too early.
Oh, whether I am supposed to use mine? We were expecting you to be here. Is there a speech? Hello, can you hear me now?
I can hear you, yes, well.
We were expecting you to be here and wanted to listen to you, but we miss you.
Yes, I likewise. You know my story.
I know. We are missing your photo presentation and so many things, information from you.
Yes, it was really strange situation that took place, and anyway, I will not repeat it, but I only say that I was stepping in, we were stepping into the airplane. And at that moment,
why don't you take a revenge trip and come maybe after a few months in the summer?
Yes. Okay, so that was anyway. Life goes on. So I really have noticed that you have quite a big crowd there. You have talks from morning to late evening.
Yeah.
Many speakers.
Every time I say that there won't be parallel session or long sessions, but ultimately I end up with having something of that same kind.
Yes, very good. Have you had time to sleep properly during the conference? I guess you have been extremely busy.
Yeah, I transfer my headaches to my other colleagues, Uma Shankar and others. So I comfortably sleep.
Good.
Asha, want to take over? Yeah, I'm coming back again.
So welcome to the delegates of ICLA 2023. And today we will be honoring Professor Punchanan, who is available online. We actually wish to honor him in his presence, but we couldn't do it due to some unavoidable circumstances. Over to you, sir. So I call upon Professor K. Manjunatha Prasad, the convener of ICLA, as well as the coordinator of Karens, to do the honors.
Okay, physically he is not here and I cannot make arrangement of honoring him or felicitating him. So you miss a shawl. So I'll preserve it with me and give it to you when you come next time.
Okay. I very much look forward.
Yeah. Professor Simo Puntanan, he is my very old friend. In fact, during my younger days, way back in my ISI, Indian Statistical Institute, in 87, I was there as a research scholar, and within maybe, am I right, Simo, that we met in 88 or 90?
I have to figure this out. In Delhi, we met in 92, December in any case.
Bangalore you came, remember?
Bangalore, 93, 30 years ago.
No, 93? Okay. He must be correct. So
yes.
We together, and since that day we became sort of friends. Though there is some age gap, he is quite, he is always be very active and he can be friend to anybody. So he became a friend and then later continued. And though we worked in some common area, we did not collaborate much, but still in the life we stay together in many occasions. Mm. Today's day is with the statistics flavor, and Simo is a leading personality in Europe, and for most of the activities at Europe, he becomes instrumental. And uh, in Poland, Spain, or wherever it is in Europe, you will find him as him in the organizing committee, and he takes a leading role. So in 2012, when we wanted to form a team, as I said earlier, so after Bapat, another name that I got into my mind is this Simo, my old friend. With the help of his network, large network from Europe, he helped me. So our care, not care, ICLA network extended with his network, and many people have come in CMT, GM, 2012. Okay. Then continuously he was with us for all the things, and he used to guide me along with Bapat and Kirkland, and continued. And now we are at the stage now. In fact, I mistaken earlier that he will be at AIT very soon in the next year, but still one more year to go, isn't it?
That is absolutely. I told you that I look older than I am.
Yeah. Still, I wanted to take this particular occasion to thank all leading personalities, and today's day is dedicated to him. I must brief something about Professor Simo Puntanen. Now he is a visiting professor at Tampere University, Finland. His research interests are in matrix methods in statistics, generalized inverses, canonical correlations. He is having a wonderful book on matrix. Correct me, Simo. It is matrix methods. No, matrix tricks.
Yes, matrix.
Matrix tricks. So it is a wonderful book for any statistician who like to use generalized inverses or matrix related techniques. One must look into that and have good knowledge of that. That makes your life very simple with all those tricks he mentioned in the book. He was a senior researcher at Academy of Finland in 1992-95. His main research interest lies in matrix methods in statistics, with the particular emphasis on linear statistical models. He has published more than 130 papers, co-authored 2 books, co-edited 8 books, and 16 journals, journal special issues, and is a member of 4 journal editorial boards. The lists are quite big, that's why I'm not naming everything. He has served in a scientific or organizing committees of 65 conferences and workshops jointly with George P.H. Stan. He is a founding member of a series of international workshops on matrices and statistics. The IWMS, whatever I organized last time, he was quite instrumental, and he was a leading figure in that particular IWMS series. So he's the one who given an opportunity last time to organize that particular conference along with beside our ICLA and many of his colleagues, our friends, in fact, they have. I'm sorry, they haven't come because ultimately we ended up with having a hybrid kind of conference, and only 1 or 2 from USA, they came and joined us. The rest have joined through online. Simo, thanks a lot for all your support and joining us for all these years. I'm sure that for next 2 years we have lots of work attached to this particular conference. We still work together, but not
I'm ready. I'm ready.
yeah, not just we two together. I'm talking in terms of we four as a team. Okay, so we
Yes.
have a good amount of work lying in front of us related to this conference. We are going to have four different publications, as you know.
Okay.
So we continue, but still in a conference, uh, I won't say it is last, but if it happens to be last, then let us see what happens. Okay.
Okay.
Thanks a lot for everything, for your support, and I'll keep your shawl with me. And when we meet next time, I'll give it to you.
Okay. Thank you very much, Prasad. I really very much appreciate your kind words. This friendship and these visits to South India have really meant a lot to me and my wife. Thank you very much. So much appreciated. Had I come there, I would have slept longer in the morning.
So,
That I can tell you.
if you want to address the audience, you please proceed. If you want
Okay.
to talk anything, yeah, please.
Pardon?
If you want to address the gathering here, you
Okay,
can.
okay.
Yeah, please. Proceed. Yeah, if you want to speak anything to Papat or somebody or to the audience, you please proceed.
Oh yes, the one thing I wish to mention, I very much liked yesterday morning the inauguration session, the talks describing the history of your Manipal meetings. That was very well given. Papat very appropriately was going back to the history of these meetings and showed high evaluation for your work. There I can see Prasad is not anymore sleeping like I am sleeping here. It's so early here. Anyway, that was very nice work. I recall that in 2014 Papat made it to 60, right? I
Yeah,
think
right.
so. Yes. So 1 year from this, he will have another number figure describing his age. Anyway, Papat has been very pleasant
Yeah, in fact, we'll be
operator.
celebrating his birthday tomorrow. I shouldn't have revealed
Okay.
it, but since you brought that issue, I'm telling you.
Okay. Fine.
Yeah, following this discussion, Dietrich and Hazlitt will be delivering a talk. You should not miss.
Okay.
Okay then.
So okay. Say again. I could.
I told you the
Yes.
Dietrich and Hazlitt are here, and they
Yes.
will be delivering talk after this.
Aha. Yes.
Yeah,
Okay. Yeah, that I know. Yes. I definitely I will be
yeah.
following that with great interest.
Yeah.
Very good.
Okay then. See you later.
Yes. See you.
Bye.
Thank you, sir. And thanks to Professor Puntanen for your immense contributions to the field of mathematical sciences. So now, next we move on to a plenary talk. And today's plenary talk will be chaired by Professor Dietrich von Rosen. He's from the Swedish University of Agricultural Sciences, Sweden. I request you, Professor, to come up and take your seat to chair the session.
Yeah, yeah. Since, it's the physical, yeah, we can.
Yes.
Maybe we'll have early lunch break today.
Okay. Yeah, good morning. Good morning. It seems that we are 15 minutes before scheduled time. So we can do a lot of fun here. We can hear more to Steve, or we can have an early lunch, or I don't know.
Yeah.
Anyhow, my duty is to introduce now Steve Hazlett from New Zealand. And of course, I got some handouts here from the organizer. But
You don't require that.
I will not read it. I will say a bit when I just recognize what has been going on, when I have been known Steve for a pretty long time now. We have met in Thailand, met in Sweden, met in Poland, I don't know, on many different places. And there's maybe a reason for it. No, but and from my point of view, you, Stephen, are a bit different than most of us here, and that you're playing on a very broad scene. And I mean that you have a academic basis background, and then I will come further. So your background, I think it's mathematics, statistics is one of the pillars, but maybe mathematics also and other. And you've been working, published pretty much, and published with Simon about linear models and mixed linear models and things connected to it. And then you also have been working with something called small area estimation. And small area estimation is a pretty funny subject in the sense that you mix two probability spaces. You have survey samples, and then you have usual modelings, and you get information about. And yeah, Steve can talk more about what small area is. But this was the reason I think we met in Bangkok, where there was a conference on small area estimation. But what I think make you a bit unique is that you are active consultancy, and you have been working in extremely many areas related to what you find at the university. I think your whole university could have all the different faculties and departments could fit into your CV. But as you are a professional consultancy, and you're also a formal chartered statistician from UK. And it doesn't mean that you have a license to kill if you think about bomb, but you have a license to analyze data, which will be accepted by authorities on many levels. And there are not many of us who have this kind of broad and say academic background, but the contact with the society, which so this was second. And the third thing, which is so pretty fascinating, is that you are working on international organization, United Nations, and in particular in Asia. And what is Southeast Asia, and you even worked in countries I didn't know existed, at least not the English term. And this makes you also very unique, that you leave the local university and go out on the international level and working in really organizations where you also then will have a direct impact on societies outside New Zealand. So it's interesting to see. Not many have done it, in fact. So, and then finally, I have just to noted here that you have been the president of New Zealand Statistical Association months, I cannot say the years now. And you also have been a managing editor of the Australian and New Zealand Journal of Statistics. So altogether, happy to share your session, and I think the floor is yours now. So please. Stefan?
Well, thank you very much, Dietrich. I felt my life flashing before me as you were talking. I'm sure there's more of it, but Dietrich hasn't time to go into that, and so I'll begin my talk. Now, I thought what I would do, because I thought what I would do is, rather than introducing the topic to begin with, I realized that quite a number of people at this conference are not statisticians. I'm not sure how many of you there are in the room, but I thought instead of launching into the detail of what the talk is about, I'd give a brief introduction to what linear models are and what some of these terms mean. Before doing that, though, I would like to comment that I talked on this topic, or a topic very related to it, in 2021. And I've been working with Simo for some years, but afterwards Simo took an interest. And I think since then we've published, Simo can correct me, 4, 5, 6 papers around this topic. And so I'm going to try and pick out parts of it rather than try and give you an in-depth view of every piece. There's simply not time. And what I'm going to talk about is linear models where we're retaining the estimates, but we're changing the underlying metric. So rather than dwell on this page, I'm going to move on to some context. So here's a linear model. Everything in there is either a matrix or a vector. The basic idea is we've got something we've got to measure on, y, which is a vector. X is a matrix. Beta is a vector of parameters, and E is an error. And the idea here is that what we're trying to do is use the information in X to understand what's happening with Y. So there's an underlying metric in here, which I'm going to call V0. The error process has a covariance structure. In other words, it's got a second order properties, which it has a mean of 0 and a covariance given by V0. So we'll do the simple situation first. So X is full rank. So what might X be? I'll go back to the other slide for a minute and just talk about this for a minute. And I'll give you an example from small area estimation where we fit such models to survey data. I won't go into the complications of that, but the point is that Y might be something like, if you're dealing with something like stunting in children, it'll be something to do with height for age. Right? And this will be put on a measured on a scale that indicates what height somebody should be at a certain age, and it will produce a score, whether someone's below or above the level. And it's these scores that go in as Y. So what goes in as X? Well, what goes in as X is things that might be personal or household characteristics. You know, there'll be the sex of the child. There'll be information about the type of household, things like roof type and floor type and wall type. There'll be information on education. Mother's education is almost always critical. Please remember that. Mother's education drives so many things. It drives family size. It drives how the way people behave toward their children in terms of emphasis on education rather than numbers. Very important, but I digress. But the point is that these things are in X, they're columns in X. So we've got a number of different children as the length of the vector. We've got X, we've got a number of measures, and the beta coefficient measures how much effect each of these has on Y. So we're particularly interested in what beta is. And we're particularly interested in the predictions that we might get out for y, given we've got an estimate for beta. So we start with a simpler case where X is full rank, and we've got V naught equal to sigma squared times the identity matrix. And it turns out that we get this estimate beta hat, and it's called the ordinary least squares estimate. And it has the property that you cannot essentially cannot extract any more information out of X. You've got everything you can that's going to be allowed you to predict Y, providing you've got this linear model. And you get an estimate for how accurate it is, the covariance of beta hat, given by sigma squared times X transpose X to the -1. And we can measure the sum of squared errors, or the error sum of squares, which is actually a measure of how accurately we're able to predict Y. Of course, this is the simplest possible situation. And if we were to put, for example, we could use this to estimate the mean of Y. If we were to put X equal to a vector of 1s, what we get is 1 transpose 1 to the -1. If the vectors of length n, that's 1 upon little n. X transpose Y is now sum of the elements in Y. So we're summing X transpose Y will sum up all the elements in Y, and X transpose X to the -1 in this case is a scalar equal to 1 upon n, so we get the mean. But this can be extended, and so one of the simplest cases is fitting a straight line to a set of data that graphs X against Y. So again, this beta hat then contains the best estimates of the intercept and the slope. So the extension is sometimes we have a different underlying metric. The covariance of the error provides a metric. And if we've got a full rank X and V naught for the moment, what we get is the best linear unbiased estimator, the blue. Now, the reason I'm saying this is because I've given a talk similar to this before, and halfway through somebody asked me what a blue was. I thought, well, perhaps I better start at the beginning. So so far, I think we've covered a reasonable amount, not necessarily in this form, but sort of undergraduate statistics course on regression. So X is sometimes full rank and sometimes it's not. And it tends to be full rank in situations where you're doing a regression problem, but it tends not to be full rank in situations where you're doing experimental design, where what's an X tends to be 1s and 0s indicating treatments or blocks or something similar. Nevertheless, this underlying metric is pretty important. This V naught matters a lot, because if you change V naught, you generally change the estimates that you get out of the beta, and you change the covariance. And you can see that this is not a particularly straightforward function in terms of understanding how you might be able to change your data in a way that gives you the same estimates or the same covariance structure. I mean, if you take a straight line, you've got a number of data points around it, and you move one of them, you change the line. So is it possible to change your data in such a way as the line stays where it is and the covariance structure for your estimates stay as they are? Or, as it turns out, alternatively, the sum of squares of errors remains the same. So that's the background. So what we're going to do, I now have 4 slides, and I'm now on to the abstract. We could be here a long time. Okay, so now that I've given you that arrangement, the question of how you can change the model and change the underlying error structure and still end up with the same blues was answered by C.R. Rao in this 1971 paper. It's a very interesting paper. It's quite long and it contains an enormous amount of detail. And yet this particular stuff occupies about 2 pages of it. It's it's not the main focus of the paper necessarily, but it's a really important and central result. So I'll show you the condition, the way you can change your original covariance structure V naught, the way you can change that, and I'm going to be looking at what his results were only about retaining the actual estimates, the blues. They weren't about retaining covariances. They weren't about retaining error sums of squares. So that's the material that Simo and Jaco and Augustin and I have been working on. So what we're trying to do is we're trying to retain the same blues and the same blue covariances, but we're trying to retain the same blues and the same Iwsmga squares. And when I think the key references are this one here from CRL, and there are a couple of papers that one that I wrote with Simo and one that I wrote with him and Jaco and Augustin that appeared in the recent volume, which Prasad will know well, and others look at this one. Then I'm going to look at what's the use of this. Now, I'm not going to argue for a moment that use is everything, but I do sometimes find that being able to turn things into a situation where you can use them for something, it often persuades some people that it may have been worth all the effort.
Yeah.
So here we go. I'm going to, having established them, I'm going to look at results related to data confidentiality and to encryption. And if there's time, I'll mention some genetics applications as well. And the key result for the data confidentiality is that what we can do is that we can not only look at retaining the blues and retaining covariances or retaining the Iwsmga squares, but we can actually create new data sets that don't look anything like the old ones that will produce the same results. And we can do this in a way that will allow us to, at least for the retaining the covariances as well as the blues, it will allow us to look at every possible submodel. What that means is you start deleting out columns out of X. You can delete as many columns as you like. You can delete them in any order, and you'll still get the right parameter estimates for that submodel. So I'd originally done some work on this sort of data cloning problem, which is the one of having new data sets that have some the same statistical properties. I'd originally done that with Raj Govindaraju, who is a colleague who was also at Massey University with me. And there's three references I'll give shortly on confidentiality and encryption, which have been mentioned. There is a data cloning literature, and you'll find the terms used in many different ways. The simplest form is simply to take your data set and reproduce it many times. And this is often used in, or can be used in Bayesian modeling in order to establish, well, maximum likelihood estimates. Because you basically swamp your prior by having many, many copies of your data. But in itself, it's not particularly interesting. What we're looking at is ways of changing data sets so that they don't look anything like the original, but they give the same statistical results. And that's quite a big area that extends beyond the area it's what we're talking about in the paper. So I'll give you a relatively simple little example. Here's a vector y. It looks terribly like some sort of polynomial with error. So what I put in X to sort of emphasize that is a column of ones that basically will set up an intercept. Next column will look at a linear term, and the next will look at a quadratic. And then we've got X, and we've got this Y new and this X new. The Y and Y new don't look very like one another. They're sort of similar, but they're not quite the same. And X new don't look exactly like one another, although they're slightly similar. I'm also going to consider this. I'm going to use that as a full model. I'm going to look at what happens as you start deleting rows and columns. So what happens is for the blue for the original data is this. So the intercept's 2.4. The linear term is 3.2. Quadratic term is 2. If we delete the quadratic term, what we get is a new beta hat, minus 11.6 and 8.8. And finally, if we just look at the first column, and we basically estimating a mean, the answer is 14.8. Now, the thing is here that both those data sets here, Y and X, or Y new and X new, will give exactly those same results. And what's more, it's not just the blues are going to be equal, we're going to find that the covariances of those blues are also equal. And it kind of looks like magic. You know, where did these numbers come from? So what I'm going to be talking through is partly where they come from and partly some more general results. So as I've said, if you use Y nu and X nu, you get exactly the same blues and exactly the same covariances for those blues as for the original data set. So we're going to return to the example later and I'll show you how it worked. It's also possible, as I've said, to create data sets with the same blues and the same error sum of squares. But this has limited application with submodels because the error sum of squares can only, to retain this, we can only look at situations where there's a very limited application. It's not possible, I'll explain shortly why, to change the error covariance matrix and retain the blues. That part's fine, you can do that, but you're either going to retain the covariances or you're going to retain the error sum of squares. Can't do both. So I'm going to consider, since I want to look at submodels as well as an original full model, I've got a full model here, which I'll call M12, given by equation 1, and the other one, which is the reduced model, or the small model, where we've deleted some of the columns of X from the original design matrix X0. And the covariance structure V0 we assume for the moment is going to be the same for both models. So I use the 0 to indicate this is the original model in 1, because we're going to have to do something with the second term in that in order to make it orthogonal to the first. Housekeeping. I'll just leave that up long enough for you to glance at, but it's pretty standard. We've got a vector Y interdimensional. We've got a covariance matrix for E, which is V0, which is equal to the covariance of Y because this is a fixed effect model. Our expectation of the error is 0. We've got X1, which is n by P1, X02, which is n by P02, and the sum of these two things is equal to P0. So that means it gives us the size of X0. And we may, in this case, we're going to partition X0 into X1 and X02. They're not necessarily a full common rank, the design matrices X, and the parameter vector I've just divided up in the obvious way. I'm going to let mu equal X0 beta 0 just for convenience. All right, so we've got generalized inverse, the more Penrose inverse column space, orthogonal column complement to the column space. So I'll be talking about A perp, meaning the matrix is orthogonal to A. I've got a projection matrix here, orthogonal projection with respect to the standard product onto the column space of A. And we can look at the orthogonal projection onto the column space of A perp, and we'll call it QA. I is the identity matrix, and often in here we're going to let A equal to X, and consequently we've got we can define M and M1 and M2 in the following ways. So the obvious choice for the matrix that's orthogonal to X is M, which is IN minus PX. So here's Rao's result. He said, we start off with this model, which I put up before, Y equals X beta plus error. And the necessary condition is that the new covariance matrix, the new metric, is given by the original one, plus a term X transpose AX, sorry, XA X transpose, and another term, which is V0 X perp times B X perp transpose V0. Now, Rao only commented on what the blues were. He made no comment about the covariance. He made no comment about the error sum of squares. But it turns out that actually these two terms, the two terms that you add on, if you add on one of them and not the other, you can get retain the error sum of squares. That's if you add on a term like XA X transpose, you can retain the error sum of squares. And if you add on a term, the last term beginning with V0, only to V0, then what you get is retention of the covariance structure. If you add on both, you don't get retention of either. You get the blues, but you don't get the retention of covariance or error sum of squares. And you can start to see from that why it is that you can't have both properties. Because you add on both terms, you lose the covariance advantage, and you also lose the advantage of retaining the error sum of squares. Now, in most of the work that we've done more recently, we've looked at the situation where what we're adding on are two quadratic forms. And the benefit of this is we can then get that V must also, if V naught is positive semi-definite, in other words, its eigenvalues are all greater than 0, then so will V be. And that's a nice property to have. But actually, if you go back to Rao's result, there's no such requirement at all. And there are situations in which what you add on there is not a quadratic form that gives something that's positive semi-definite. What you're adding on is something that may even be negative. And it turns out that some of those situations occur in genetics. They've got a very useful application because in genetics, you've got an enormous amount of data. And it may be that by changing the covariance structure, you can make the algorithm that you're running on your computer work much more efficiently. So there are questions about how to go about doing that, and some of them involve looking at situations where you're using matrices with negative eigenvalues. But let's start with this because it clarifies a number of issues and allows the whole topic to be outlined with greater clarity than dealing with these rather interesting situations where you don't have this positive semi-definite property for V. I thought it was about time for a diagram. So if we look at that first, the first model that we talked about, the full model, where we had beta naught, we had beta 1, and we had a beta 2. This is a way of diagramming what we're adding on. Now, it's not quite the same way as what happens with matrices, but the idea of this here is that this is adding on a term in x1 times the matrix times x1 transpose. So this one corresponds to a cross product term, and this one corresponds to a cross product term, as do this and this. And the interesting thing about Rao's result is that basically it's excluding certain types of cross product term. So if we look at this model taken on its own, the things that must be 0 in Rao's result are the things that are in yellow. If we look at the reduced model, the small model, the things that must be 0 are again in yellow. And we can see that these two things don't coincide. So if we want them both to operate together, you can start to see where this is going. That this area in green here is exactly corresponds to this area in green. And if we were to set that area, if we were to allow terms that were basically in V naught x per times a matrix times x transpose per times V naught, which would be this term will give us the green area here, and all the rest will be set to 0. And that's kind of where it's heading. So these are ways of diagrammatic representation of Rao's result for the two different models. And you can see that they're different, and you'll also start to see how we might have something that we could use and add on to V naught that would work both for the full model and for the small model, and as it turns out, for everything in between. So this is material I've mentioned before. In a way, we're staying with A equal to U transpose and B equal to UR transpose. And we need to replace certain additional restrictions, as you've seen in that diagram. If we want to retain the covariance of the blues, what we can add on must be of this form only. And if we want to retain the error sum of squares, the two we add on must be of this form only. But if we add them both on, we don't get to retain either the covariance structure or the error sum of squares. So the result can be found in one of the references, which is here. We've not yet It's under review at the moment. The paper's not complete. So I just want to emphasize what I said before. So I'll just leave you for a moment to read this through. But basically all it's saying is that what we can add on to V0 depends very much on the properties we want to retain. Browse condition gives what we can add on to a particular model, and what we can add on is basically a term that involves XA, X transpose. If we want to, and the term which is involved V0 X per. And if we add one of them on, if we add on the term XA, X transpose only, we can not only retain the blues, but we can retain the error sum of squares. And if instead we add on the term in V0 X per, what we get is retain the blues and we retain the covariance structure for the betas. So that's essentially what all of this says. So these require, they're mutually exclusive, except in the case of no change. In other words, just leaving V equals to V0. So it's not possible to change the underlying metric and retain the error sum of the blues, the error sum of squares, and the covariance of the parameters. It's just not possible. Now, retaining error sum of squares might also mean that you retain the residuals to the model. By the residuals, I mean the distance between, or the differences between your Y value and your predicted value, which is going to be X beta. So it may be that in certain circumstances, it's possible to retain those. And the example I put up earlier, if you just look at the linear effect, the intercept and the linear effect, and you add on to V0, you add on X transpose, so A is equal to the identity, then you can construct an example where you retain not only the error sum of squares, but the residuals. And I'd rather hope it would be possible to do this more generally, but the answer is it isn't. There's a slight peculiarity about starting off with a model which has got an error structure which is independent, like sigma squared times the identity matrix. And the odd thing about it, or the very nice thing about it, is you can choose your eigenvectors to go in any direction you like because all the eigenvalues are equal. And that's not generally the case with a general V0. So you can't get this retention of the residuals as well. I've been rather hoping that if I could do that, then I could construct data sets that would give you everything you wanted. You'd be able to retain, if you're able to retain the residuals, you'd be able to use them. You'd be able to provide data sets which were not the original data, but the residuals were all there for the model checking. However, no such luck. So with blues and their covariances, the earlier slides concern retention of the blues under changes of error covariance. Blues are estimable functions. The covariances of them are not conserved, even for weakly singular V0. Now, by weakly singular V0, I mean that the column space of X is contained in the column space of V0. And when I did the original work, I needed that assumption to make my results work. And Sema went away and, of course, worked on this and came back with the fact that actually you don't need to have weakly singular. You can use this for any covariance matrix. And the big advantage of that for me is that it involves far less checking of what your structure is for V0. In the case of genetics problems where the V0s can be huge, where the covariance structure matrix can be huge, this is a big advantage because you don't want to have to spend a lot of time checking covariance for a particular property before you begin on the procedure. So what we're going to do is look at, as the example, we can limit the structure, so we're going to look at the covariances only of the blues being preserved along with the blues. And then we're going to look at the full, intermediate, and small models. So it's possible to ensure that for each of these models, we retain the blues and the covariances under changes in the error covariance. You'll see that when you knock out a column of X, of course, the blues do change. What I'm saying is, with this covariance change, they'll change in the same way each time you delete a column. So what we're going to use is this. It's a restricted form of V, which looks like this. Now, when I did this work originally, I was trying to look. I looked at. I could establish this was a sufficient property. I wasn't too focused on whether it was a necessary property, because of what I was doing was trying to use this for data confidentiality. I mean, in a sense, just eyeballing it, there is a sense in which this must be so, because the other term starts to affect the model in a way that you can't retain the covariance of the blues. But SEMO again went away, and this is a necessary and sufficient condition. If you want to retain the blues and the covariances of the blues, then V must have the structure. End of story. Now the difference, the possible thing is here that what he was working on was the situation where you're dealing with a full model only. So this is the right equation. But it turns out the reason I was not so concerned with the necessary condition is when you start looking at submodels, there are other possible structures that you can put in here for X. In other words, you can include more things because you've deleted a column out of X. You've deleted some generalist, there's multilinearity. You've got something you can add to X perp. There's something you can add to X perp. There's a matrix here that's got a bigger dimension that you can put in for the submodels. But I wanted to focus on something that would work for everything. And if it's going to work for everything, not full model, all the way down to the small one, it's this structure that you need. So what we've done here essentially is this. The yellow parts are the parts that must be set to 0 on the basis of Rao's conditions for each of these models, the full model and the small model. We'll talk about intermediate one shortly. So that's the yellow part. But if we also set the orange part to 0, what we're actually doing is we're focusing on the green part. And that's the part we're adding in this equation here. It's the green part in that diagram. And if we use the same green part for both, we can get things that we can get a structure that will work, or an addition that will work, which is this one here, which is related to X12 perp. It's related to this part and not the part which is related to X perp in this small model. It's not this. We're going to focus on this in both models. And if we do that, and we only add on a term of that type, then what we're going to get is we're going to get something that will work for the full model, it'll work for the small model, it'll work for everything in between. But that was what was in the example. 8 minutes. Okay, so we've got the covariance properties. I just wanted to illustrate this with full rank situation so that we see what we're looking at. What we're basically saying is the covariance of the blues under V and V naught, when V naught is full rank, is basically given by this. And they're both equal to one another. The only difference between this and this is this has got V and this has got V naught. So that's retention of the blues. You can sort of see this as a in this simple case where V is invertible. And basically it's just a little bit of algebra, and you get to the point where you find that the two things are equal. Of course, their inverses are also going to be equal, and that's why the covariance structure is equal. You can extend this to extended it to the weakly singular situation. SEMO went away and extended it to V being fully singular. And that's the argument here. So we can extend this to weakly singular. We can extend it to singular matrices V naught and V. We can do something with mixed models as well, but I don't think there's time for me to talk about it, except to say that there is a handle on this. There's this sort of structure that we can use for a mixed model in which gamma is a random parameter, beta is a fixed parameters. We can certainly look at that to produce the E, the last two terms, and look at the fixed effects. There's no problem with that at all. But if you want to get a handle on retaining we've done. There's a paper published on retaining beta and gamma, but the work on just retaining gamma is in progress. So the idea is that this can be extended to mixed models as well. So we can add and delete either fixed or random parameters. Comment, this assumes that the V naught, U, and R are null, which is seldom true. And if I get time, I'll return to that issue. But these, if you have a particular estimated covariance structure, the principle is that it's estimated. You can treat that as what is you're given. The algebra follows in the same way. So we're going back to the example and uncover the trick. So what we did here was we just used ordinary least squares. And in the example, we allow models to be reduced down to the simplest form, e.g. only an intercept. The only term added to V naught to create V is of this form here. So x1 to perp is it belongs in the column space of the errors. So this is what we added. And we used this new full rank V. We used the Gillespie or the square root of its eigenvalue decomposition, V to the half. We pre-multiply it by V to the half. Different selections of U can produce an infinite collection of data sets that have the same regression coefficients for all submodels of the original data, as well as the same parameter covariances, estimate covariances. So what we're doing here, we just multiply by V to the half because we don't need to multiply by the original V naught to the minus half because it's just the identity. And what we get is this, and this is how we produce new data sets. This can be extended if we look at the situation where we've got V naught in its full rank. First of all, we multiply by V naught to the minus a half to produce data it's basically independent, and then we multiply back again by V to the half. So this is basically the mechanism by which we produce new data sets. We can also do it if V naught is not full rank. So what we get out of this is that we get a new data set, which I've put a C on to indicate it's cloned data, where the parameter estimates and their covariances are retained for not just the original full model, but for everything down to the no model, almost no model at all, the intercept. So again, the results can be extended from weakly singular V naught to any V naught. I'm going to skip over this slide in the interest of time, but the idea is that you can also retain error sums of squares. It could be useful for looking at residuals. I've been playing around with this mostly with examples. It's a little bit complicated because retaining the covariance structure for the parameters does give a lot of latitude to what happens to the error sum of squares, consequently what's happening to the residuals. So it may be that the need to look at ways of moderating that. I'm not quite sure what the answer to that question is yet. And I haven't tended to focus on retaining the error sum of squares, because although Rao did use V naught plus XX transpose to deal with problems of singularity, it has the problem when you're adding on X times X naught and you want it to work for submodels, you can only add on the X for the smallest model you have. So basically all you can add on, if you're going to come down all the way to an intercept term, is something in the form of this has a vector of 1s times its transpose. Some of the matrix in the middle, it's not particularly, or some of the scalar in the middle, it's not particularly interesting. So the more important part for cloning data is very likely to be the situation where you retain the blues and their covariances rather than retaining the error sums of squares. So we can produce as many data sets as we like, and the reason that this is useful for the data visualization, smoothing, confidentiality, and encryption is that we can basically create a new data set which looks very like the old data set in some ways, but doesn't really look quite like it at all. So you will remove essentially all the information about individuals, because none of the data is actually from an individual anymore. It's a transformed version of it. But it will still give the same parameter estimates in the models you fit, so long as it's linear models. And you can set it up, as I said, in a way that will work for all submodels. So these data sets can be handed out to researchers. They can go away and do the research to discover the effect of, let's go back to women's education. And they'll get the right answer even though they haven't got the right data. So that's the key. And I should explain my interest in this is partly driven by the fact I worked in a government department for doing official statistics for 2 or 3 years before I did my PhD. So it's sort of driven by the recognition that government statistical agencies very seldom give out unit record data versus individual data or household data. But it's almost critical if you're going to do anything that's of any, it has any depth to it in terms of understanding what's going on. So there's this tension between what the official statisticians want you to know or give you and what you really need to know in order to come up with some useful results. So this is a possible way, at least for linear models, of avoiding that problem, because the other way of doing it, or the I diverge slightly. The other way of doing it is producing what are called confidentialized unit record data, where they simply add on error to everything, and they remove usually all the area information, so you don't know where anyone's located in order to have confidentiality. Not particularly useful if you're trying to do small area statistics, because you don't even know what area anybody belongs to anymore. So this may provide a way of including area information in this one of the columns in the, or a set of columns in the design matrix X, and we can confidentialize the data in a way that can get out the correct answers. So that's really what this slide's about. There are, of course, some problems that are unresolved that need working on, but every time you solve a problem, you find out, I find there are 3 more. And the underlying problem is often when you're doing these things, if you're fitting a mixed model, for example, it will be iterative. So what needs to be provided in that case is the data sort of one step before the final solution, and to change the covariance structure for that. And a similar mechanism may work for generalized linear models, but I'm conjecture. I'm not sure. But the idea is that you can go back from the last step 1. The problem with doing it otherwise in an iterative process is that what you actually need is not the information you have currently to hand if you're working with this. So you need the information from 1 step back, which you don't have unless there's an enormous amount of additional information provided with confidentialized data. That's basically what's here. If we've got an iterative if we're using iterated generalized least squares, or we're looking at generalized linear models, there are some complications that are unresolved. If we're going to use estimated covariance matrices, it's fine as long as we specify what they are. You know, we can have a V0 hat, that's fine. And what we find out is what models we get for a new V hat. We just put a hat on it, the algebra works fine. We can do this for different dependent variables, possibly, but there are some twists. You've got to be a bit careful that you don't include the dependent variable for one model as a regressor in another if you're trying to use the same data set. So that's basically about this interchanging Y and the columns of X. Difficult. So what you're better to do, if you've got 2 variables you want to predict, you know you've got 2 of them, basically exclude them from the X, and then you might be able to have an X that does the prediction for each of them separately. But at the moment you include one of them in that X matrix, it makes it impossible basically to have the same data set that will be usable for both. So but the point about this is that what you're trying to do is restrict the number of cloned data sets you've got to give out to a particular researcher. The good news is there is so much adjustment in this that it's possible to have any number of data sets where you give different researchers use different V's starting from the same V0, use different V's, they get different data sets. Even putting them all together is not going to help them much find out what the original data was. So these are alternatives to curves, for example. Now, curves, as I said, are often data sets provided by government statistical agencies where they think they've confidentialized the data so much you'll never work out what individual corresponds to a particular observation. However, they do this, as I said, by adding random error. If you add random error, then the results are no longer, there's no longer real results. And there is remove this area information, which makes it almost impossible to be useful in any real situation when you're trying to get down to local estimates. For encryption, well, the idea is basically that you can use this, even if you think nothing about regression, you know nothing about it, you can create a new data set from which you can't recover the original data set. It's a form of encryption. I talked a little about this. I'm just going to emphasize the last point and finish. What's essential to understand is that we seem to have got an apparent increase in statistical power from combining multiple copies of cloned data. It's not a free good. It's a consequence of changing what we're doing. Normally, when you do a regression, you take the data set you've got and you fit a regression. What this is doing is it's searching across the set of all models that produce the same parameter estimates as the original data does. So it's changed the structure in which you're doing inference. So it appears that you're getting something for nothing. You're getting this enormous number of new data sets. And in a sense you are, but you're only getting this as a consequence of allowing that the data may have been different from the data that you had originally. It's not a, it's not, as I say, it's not a free tool. So the acknowledgement is to the, as my final point is the acknowledgement to the workshop that was held in 2021. And of course, to my co-authors, especially Simo, who's hiding in the background there somewhere. So thank you all very much.
Yes, thank you very much. A very broad and interesting presentation. So the floor is open for comments and questions, please.
Obviously, far too early in the morning.
Yeah, this dinner yesterday evening. No, okay. That, yeah, please.
Sure.
How can you use it for data encryption? Can you elaborate?
Well, the basic idea is that somebody starts off with a data set. I can create a new data set, which doesn't look like the old data set. That data is encrypted using the covariance matrix as the key, or the new covariance matrix as the key. If you don't know that new covariance matrix, you're not going to be able to reproduce the original data. So in that sense, somebody who's got the key can decrypt the data, no trouble at all. But somebody who hasn't got the key doesn't stand much chance. And the reason, if you're looking at, you know, if you've got a data set that's n by p, where p is less than n, then and the covariance matrix is n by n, you're not going to be able to recover it very easily from your x new matrix. So the idea basically is that we're basically moving all this around in a very particular way. We can change every data point simultaneously in a way that will allow us to recover the data by reversing the process.
Okay, and more comments or questions? I have then a very general question. To me, linear models, everything is about the linear spaces. And you mentioned column spaces here and there, but you never really, I have a feeling when you want to change your data, you want to get the same estimate. And somehow you should stay within the proper column space. Could I formulate things in these terms, or is it not true even?
Well, I think that even if you go back to Raoul's, Raoul's original result, I mean, he doesn't change. He's looking at y equals x beta plus error. Nothing's changed there. He's just changing the metric that you're measuring it in. He's changing v0 to v. And v is what's being added on to v0 is in the column space of x or the column space of v0 x perp. So I'm not sure that we're adding any additional column spaces.
No, not it's shame because I think the final result is about projections.
Yes.
And that is connected to the space. But of course, if you're changing in a product with V, that has an impact, and one should maybe understand it. But later, so when you go over to residuals, because residuals are usually something orthogonal to the mean space, depends how you define them, of course. So therefore, so if one formulates things in linear spaces and the compositions of linear space, because this is also when you look at singular covariance matrix, that it's pretty important to have this decomposition there.
Yes, I'm not quite sure which decomposition you mean, but I think a lot of this gets retained. That's why you're not allowed in Raoult's result to have a cross product term in X and X perp. And the reason is that these basically confuse the space, the two different spaces, the one that belongs with the parameters and the one that belongs with the errors or the residuals. And so it's keeping these, basically the result seems to me to be saying, we've got to keep these separate. We can't add on anything that basically confuses the error with the parameter space or the column space for X. So it's keeping those separate, and I think that's why the whole thing works. At the moment, those get start to overlap, all this falls apart. So it is still about keeping certain column spaces distinct. And the one that needs to be kept distinct is the one that corresponds to the model, which is the column space of X, and the one that corresponds to the model errors, which is the column space of X group.
No, I just a comment, because if you have a singular covariance matrix, then you combine mean and the variance spaces. Because what is orthogonal to the covariance space, it has an impact on the mean space in form that it gives some kind of restriction there.
Well, I think really the person you need to talk to is Simo, who's produced the results for this. But I think that you know, this problem doesn't occur, I think, or I didn't find it occurred with the looking at weak singularity, where your column space of X is included in column space.
I can imagine that.
Yeah.
Because then, but there's, in the strong singular case, there's something more outside.
There's something more outside. But the interesting thing is that if something more outside, it doesn't occur in Raoult's result. So there's no term that you're adding on that's perpendicular to being.
He's cheating a bit. I think.
Oh, he's cheating a bit.
Because he introduced a concept called consistency.
Yes.
So it's also about the data. That is supposed that the data is in a certain subspace.
Oh, I see. Well, I'm not.
I don't know. We can discuss it out. It's an internal discussion. So, any more comments or questions here? Okay. If not, then I will close this part of the morning session. And thank you very much.
I request Professor Rawson to hand over a token of our appreciation to Professor Hazlitt.
So I have the honor to decorate you, but it's, Christmas.
Thank you, Professor Hazlitt. Thank you so much. We indeed had a great discussion, and after this, we will have a break for 20 minutes. We will get back here after having tea at the ground floor at 10:50. We have 20 minutes break. We'll join back here at 10:50. Thank you.
That's it. We'll just stand here for 2. So thanks, I got it. Oh yeah.
Oh, and that paper, yeah.
Hello, Adrian.
Something that's essentially.
Kind of bordering and both which is you and me now.
Absolutely. I think it's you. I think I used you as to ensure that the V was also going to be positive. So that's basically,
Yes. So that perturbation has been done for keeping the V to constant.
yes, that's all, it's the whole aim of it. It's not that browse condition requires it.
Yes.
It's just that the proofs beyond that, they're hard enough. Ensuring positive semi-definites. And I think that's kind of okay. I think it basically we've made it happen. We haven't solved the entire problem. And the reason I say that is because genetics, what they want to add on, they want to use synchron matrices and various sorts on the covariance structure. And it produces negative eigenvalues for things that should be covariance matrices.
Yes.
But it works computationally. And even CRR commented on this. He said there were things that didn't look like covariance matrices at all. The computation. And I think that's kind of the issue. If you allow things to become big, you have positive semi-definite.
Yeah.
It works computation, but what on earth is this? Impossible to interpret. So the only reason we do it, I think, computational functions.
So that's why there's a small adjustment was done.
Well, what I'm saying is that what the geneticists seem to want to do is they want to start with a V, and they want it to be minutes, and they want to produce a new V, which makes their algorithms work for us. Because they're so the problem's so big, they've got a million individuals, and or rather, they've got 100,000 individuals, and they've got a million genes, and now they've got a huge problem. So you want one that the computation issues, particularly if you've got an iterative process. So they're keen on finding covariance structures that will work that save computation. So that's, and the ones they use don't obviously fit into this format. So I've been working more recently on what you do is we even put them in a form like that to understand when they won't do it, because this is obviously quite important. You know, you don't want going off as a puppy revision through the algorithm regardless of what the problem is. You want to do some checks with it. So that's basically the genetics situation.
Thank you. Go for coffee.
For the talk. Oh, well, the only data set is the one that I've used in this is the data set for in this talk. The only data set I've used is
Slides are in this.
that
is not pendrive.
The other data sets come from doing small areas. And unfortunately, I'm not at liberty because they came to me from the government. Yeah, I mean, I very much like everyone to have them so we can have some proper discussion. I'm just not allowed to.
This PDF file. This PDF file.
The presentation. Yeah, oh, well, you can have a copy.
Okay.
But,
I want to copy this.
yes, no, that's okay. If you ask,
Actually, I think properly reflect in the TV. That is a lot. Find it. Yeah,
yeah, that's right. And I think you'll.
It's
you'll
just for
find that
cameras.
It probably gives you a bit of a, maybe if you're but the papers that should have something. So the papers are, three or four or five pages. Or a side. But I think the presentation helps you understand how all of these are connected together. And, please, if you need something in the environment.
We'll have copy.
No, it's fine.
Well, possibly.
Statistics, we also work as a data science multi-million component.
Yeah.
I have to also also my institute needs this kind of files or this kind of videos so that I can also share knowledge with others. So in January you will available in India or you are going back?
Oh, I'm going.
Well, I said Delhi also organizing a conference, international conference.
Oh, I see. Well, after this, we're going to Nepal because I have a good friend in Nepal.
Okay, it's a nice place. Nepal is nice, but just place is very costly, okay? So we have to,
I've worked in Nepal.
so
That will.
if I mail you, you will share the PDF. I can take it from,
Yeah,
this is my name, Sajal Ghosh from ICT.
yes, okay.
Okay.
So, yeah, it's very nice to meet you. Yeah, no, send me an email for that, which is, that one's at the Australian National.
Okay, okay.
That will still work. If you send that something to me, I can send you things back.
Thank you. Thank you, sir. Can you please put on message on that so that I can. I am sharing my mail ID. Okay, you will send the file. Yes. Okay. Yes.
Oh, thank you.
Not having coffee? Yeah. Mute, unmute. No, it is not on. No, it is kept on. So it can hear us. It's not recording. Report copy big. Radio. So you can speak it on that. And the stucker and what stucker is inside. professionals, the practical applications and all that you are new. But I am not. I am only interested in mathematics.
Well, that's fine.
So, I tell you, I'm trying to look at these things in an integrated manner. So that all other results will follow. This my attempt. That is
The unified theory. The unified theory. What, you want one theory? So
no, it's not that. The mathematical background student is what is, when you say linear model,
yeah.
see, what is anatomy of, see the anatomy of that. That is splitting weight into components. One person not strong or somebody, yes, done that. And Chengupta and Srinivasa Rao, in their book, they are also mentioned about that. And Chengupta and Srinivasa Rao, they are also giving their own way of splitting it. That is writing Y as a sum of four ways. Only one is concerned with that the range of matrix B, various matrix in the function, in the function. And Y2 is the remaining part of B. Y3 is the component missing from this X. When that B intersection does not X, is some X out there. So the remaining part of X. Y4, that is all I minus B minus. That will be I minus B plus X and that B plus
You be here in the first of second row. Yes, yes. Better to be in the second row.
that is the one particular 2D
Take the mail.
B plus X. That is the reason in the
Everything fine. There's no more just. Yeah.
We should go prepare 10 minutes first. I will prepare the just one thing that water was speaking. Yeah, can you you want it now? Okay, nothing. Okay, the glass. You first, okay, you that. You should finish one job first. After that, you go to the second job. Yeah, that is. Yeah. So we have to inform if we are not going for this program. I don't know. I didn't know. Sriram sir, and Sachin also, you know, but yeah.
Welcome back after the tea break. All the delegates, I hope you're back. And please take your seats. So now I request Professor Stephen Haslett, whom we heard in the last session. I call him forward to chair the session and introduce the next speaker to us. Over to you, Professor.
Well, it's my pleasure to introduce Dietrich. I suspect he needs no introduction for most of you here. But nevertheless, I'll give a brief one. So Dietrich's a visiting professor at the University of Linköping in mathematical statistics, and also professor of statistics at the Swedish University of Agricultural Sciences. So the main reason most of you may know him, he's the editor-in-chief of the Journal of Multivariate Statistics Analysis, and he's also, of course, got a very strong research profile in linear models and multivariate analysis, and bilinear models, high dimensional analysis, and matrix algebra. So he's of course supervised many PhD students despite his youth. And I'd like to introduce him now, having pointed out that he's published one book already in Advanced Multivariate Statistics with Matrices, and has a new book, and I shamelessly advertise it, in bilinear regression analysis. Dietrich.
Yeah, thank you very much. We found the North Sea. The book has been out, I think, for 5 years now. The recent book.
This is the profile.
Yeah, I know. But it's good. Just advertise it. It's not so popular. No, and of course, first of all, I have to thank the organizers who have invited me here. It's a great pleasure to be here in Manipal first time. And I've been in India a couple of times, even a bit further south, but it was 10 years ago, and I've been to Kolkata maybe 5 years ago. But for the first time was 93 here, I think 93 or 94, Kolkata also. And it's interesting to follow the society, what happens. And also one doesn't see much, but one can see what happens to the cars in the streets and how people are driving. There is some kind of change, I think, going on. Okay, we should do some, or I present something to you. And in some way, what Steve did here now, it was a good introduction to parts of it. It's also about linear models here. Unfortunately, I have a bit different notation, so I should slowly introduce you. But in principle, it's the same. The linear models. But the aim of my research is to go over to multivariate linear models and what we call bilinear models, which I will probably not explain. I will not have time to it. So I just want to discuss a bit of the concept here. And I have two choices. And either I go into techniques a bit, or I try to discuss more general ideas and principles. And I will start at least with these ideas, the main ideas behind the research. And then we leave the technical things for, I don't know, for future. And now this is a pretty new topic to me, and ridge regression. And it has been available for a long time. Ridge, it really came from the 60s, started when you were calculating. It entered statistics in 1970 by, I don't know how to explain, Hurl or I guess Hurl, and Kenneth have a paper in the 70s. And then it became popular for a while. Yes, it should. But today, when you see things, one usually talks about penalized estimation. And the idea has shifted a bit. Also, the same things you're talking, the ideas have shifted over the years to what's going on now. And penalized estimation today is mostly that you have some estimation function, and then you have very vague information about the model. And you usually want to do some kind of prediction. And it's often today also that you have a lot of covariance. It was the Iwsmga, what Steve had. It's a high dimension object. And then you want to predict the response. And then in order to able that, you have more like covariance compared to independent observation. In order to handle it, you have to put some restrictions somewhere. And you cannot have more parameters than independent observation. It's not you can, but the result is very weak. So you have to put some restrictions on it. And here in the penalized estimation, you usually put restrictions on the estimation function. Today I will shift this a little bit, and because I'm so grown up with likelihood and models, so I will take everything down to models, and even somewhere some kind of similar results. I will achieve similar results and reach regression, but not what today you maybe have heard about lasso, group lasso, and I don't know, there are many types here, and most of them are in fact connected to both have a good estimation function, but at the same time select variables, just to diminish the space in some way, to do some good performance. But the object in my case is to go back to classical linear models where you have parameters, effects, this beta, which we saw before, that has a meaning. I'm not so interested in prediction. I want to understand my data, and I want to do it in a better way than has been done today. So I will illustrate these ideas in univariate linear models, and you will see a bit the connection to ridge regression. And here is really the main research where I'm interested in. But I will not come to that. It's too little. And if someone becomes interested, we can have talk later. So, so as I mentioned, if you have in what today is going on, we have parameters. We have we have an estimation function. Typical estimation function is the least squares criteria. But instead of using the least squares criteria, you penalize it. And it means in some way that you say shrink the parameters or remove parameters from the huge parameter vector which corresponds to each background variable. And this you can do algorithmic. So we modify our estimation function. But now, today, I will narrow my estimation problem by putting restrictions on the parameters, not on the estimation function. And this, I think, is a philosophical idea. I think it's much more interesting to look at it from you have a likelihood, you put restrictions on the on the parameter, then understand my model better. But the aim is here to understand the model, not to do some kind of prediction, because you can predict things without having much understanding of the model. But here's a classic that we want to study effect. Which effects are important? Okay, our restrictions here, and that's different also with this penalized. The penalizing, you're trying to estimate some kind of penalizing term. Here we put restrictions on the parameters which are supposed to be known. And that will also cause, because these restrictions will not be that they put restrictions on a linear space, I will put the restriction that they some kind of maximum or through inequality and know some upper bound only. And that will lead to some kind of Lagrangian function. And you know, in the Lagrangian function, you have Lagrangian multiplier, and that Lagrangian multiplier is in some way the same as you do when you have your penalized estimation function. And the math behind it, which I think one should, when we do statistics today, we're far too sloppy with the details. For example, there's so many algorithmic approaches but we don't know even if there's a unique solution to the problem. It just converges to something. And we know usually we have very little knowledge about the properties of these things. And this is some kind of modern, I don't know what to call it, but modern way of handling big data. But I don't think it's very mathematically, and I don't think it's not good in the long run. Because when you just have algorithmic approaches, you show things through, say, cross-validations or something else. You can never be sure, or you don't know when you can work with it or not. You come up with a numerical result, which maybe has a people are happy to find a result, but they don't understand really what's behind it. And we, as a statistician, or many statisticians, deliver that result. But we don't know if it's a good result we deliver, a bad or a correct even. So I think sometimes I would like to take 2 steps backward and start from the very beginning. And then one way to estimate is to use convex optimization theory. And this we have done for a long time before when we talk about exponential families and things. And the nice thing is that when we still have an algorithmic approach, but we know that there's only one solution to it. So in some way, we are pretty sure that we are correct with our estimators. But as a statistician, I had to learn a bit what this optimization or convex optimization is about, trying to understand. And it's not so complicated to have it get for our problems. Then, of course, when you have non-convex problems, then it starts to become you have to do approximation. And in fact, you don't need this convex optimization to find the maximum of a function. It can be convex on a local level. And then it's just monotone increasing or something like that on the outside. But this type of problems I haven't narrowed yet. So I'm a bit conservative. I keep to this convex optimization problem. And that means that I have sometimes problems with the parameterization of the models, which, because usually if you do likelihood theory, you can do one-to-one transformation of the parameter spaces. But here, when you use convex optimization, you can use a one-to-one transformation, but you can destroy the convexity by doing it, or you can achieve convexity. Okay, here are our linear models, and if we compare to what Steve have, we have completely mixed up everything. And the reason is that I want later maybe go to multivariate problems. So we have a response here, and I think you had Y. I use T for transpose. You had this blip before, and this is a vector now, a row vector, because I like when multivariate to have columns, p-dimensional columns, and then I put them side by side. And Steve does it opposite if you would do it in if you go on to multivariate. We have a design matrix C, which is known, which we last hour heard about. It was X. And then we have our parameter, which we want to estimate. And we have an error term here now. And this is a small, easy setting. And then we know that the least squares estimator, or we don't have any distribution, say least squares estimator is given here. And you see C transpose inverse, C times X. You also know that the dispersion matrix, because this is a linear function X, we know, then we have to assume something about the dispersion here, and it is IID, and it has a parameter sigma square, and then you come up to a result here. But the idea from the beginning here was that one had observed that this object here, the inverse of CC transpose, that can be a problem. Even if the formula exists, you can have almost collinearity here. So it becomes very unstable, you can become very large. So the estimate becomes, it doesn't have to be good. And it's the same with the variance. You can get a very big variance if you have something which is near singular here. And also not exact singular. So this was the idea behind, or not really, about ridge. They say that it's about, one talks about collinearity. But it was also so that in the 60s, one was very close to, one wanted to have orthogonal designs. It means that if you didn't, or you have balanced data, it means that the designs could be made orthogonal. But if you then late in the 70s to come up with unbalanced data, then one wanted to adjust it a bit so it became more balanced. And then I added some quantity, and it was, you call it regularization, and this became this ridge regression also. You will see. Okay, then we heard a lot about the best unbiased or blue, best linear unbiased estimator in the previous talk. And when I started here now look at this problem, I thought, why on earth we talk about unbiasedness? I will soon try to motivate it, that one in fact can challenge it. And most of the questions here was that you give up a bit of unbiasedness, but you can improve so-called mean square error. But here even, I think in many practical reasons, in many practical situations, and how we treat unbiasedness today is in some way unnecessary, or we are like chicken. We don't, or to be precise, we usually assume that beta can take any value. But in practice, when we really do our experiment, we have knowledge about the beta. We know that the effect cannot be too large, for example. And we know if you measure something and your equipment to measure, it works within a certain range of observations. And you never have, when you measure physical or chemical substances, you know when it works, in which range. But you cannot go out in the border because then everything will become problematic, and you have the detection limits and things like that. But you also know effects, like if you would study growth, you know you cannot grow 100 meters per year. There's a bound, upper bound, and we know them approximately, but we very rarely take them into account.
I have a question is, what kind of relationship is giving up unbiasedness and the mean square error? What kind of relationship exists?
What about the?
By giving up unbiasedness,
Yeah.
You will be. Speak on the phone. Yeah.
What kind of relationship exists that if you give up unbiasedness, then your mean square error will be improved?
Yes.
So is it an empirical one or?
Yes. And this has been known for a long time, that if you give up this mean square, and that many methods, and it's maybe not so unnatural because all variable selection, when you use the data, in some way you don't start from scratch. You are doing something, and very strictly that will affect your unbiasedness also. But then there are methods like principal component regression, partial least squares, and rigid regression also. They are all biased methods in a certain way.
So your convex optimization approaches will be useful as far as this is concerned.
Yeah, you can, and in many practical situations, they have given up a bit of this unbiased. And this is a trick when you are a statistician. You have to decide here how, and look at data, how things, what happens.
You have to give up.
Sorry?
You have to give up your.
Yeah, no. So it's not really science then. It's experience, and a lot of also how should you handle your data in some way, and there's no truth really.
Right, and we have also that experienced this kind of thing, no? That between these two. So I wanted to know that whether you have.
Yeah, and you will see. I will show you later how one can do it a bit differently.
Okay.
In certain trials. Okay, so the restrictions I'm going to talk about are given here. And this is just because it will give me, I can handle convexity in this way. And it's relatively natural, but of course, if beta would be large, I would have very little information about T. But if I have 2, 3, 4 variables, I maybe can have T, I can maybe standardize a bit, then, but it's not really useful for high dimensional problems. So when you compare it with when people today want to penalize, they have this huge data. They just have collected observations, and then I want to do something with it. This is not meant. It's meant that you do a bit more efficient and analysis in almost like usual linear models. You can do a bit more. And of course, one can, now it's just the beginning, but putting restrictions of this form here, then there can be alternatives. Here's more like an illustration of how one can do. And it works relatively well. So the mathematical problem is given here. If you have least squares. You have least squares function, we have these restrictions here. And then we know also that the function here is convex, function here is convex. You can show that by just differentiating twice. And then we saw, and when you have these convex optimization problems, then of course you use this KKT conditions. Also, so well known, I always, and I think it was Kuhn-Tucker for me when I was student. Then someone found a thesis which was published earlier, and then nowadays it's Karush Kuhn-Tucker. And I can just, he is in some way our Lagrangian function. And if we want to, we should work with it, and then we get the KKT conditions, and they are given here. So you differentiate your function and Lagrangian function. Here's Lagrangian multiply. And then we have an equation system which should be solved.
So how do you solve it?
I can solve it almost. If it's not very special situations, but I can show you soon. So these are the equations. So first we just should spell out what these derivatives are. And we should see. Here's the first derivative, and we have this lambda here. We have, and if you solve that equation, you will get something which looks like this here. And this is in fact the ridge regression, because you have this lambda. Here, the ridge comes from that you put some identity. You put the ridge inside that quantity. But there's one thing with these KKT conditions. So this is a general solution. But the most important condition is in fact here given by KKT. So called the complementary slackness condition. And if you look carefully at this expression, if this should have a solution, there are two alternatives. Either lambda is 0, or this part is 0. So from the inequality what we had before, we could solve something with equality, or we have this lambda equal to 0. If lambda equals 0, then of course this term disappears, and then we are back into least squares. So we have to decide if lambda should be 0 or not. And this is a nice observation that, and this is what we discuss here a bit, that it, in some ways data driven now, the method, because we have using data to see if we should estimate lambda to become 0 or not. And what you're doing when you're estimating, that you start to use the ordinary least squares. Take the square here, and then you check if the least square, the square of beta here satisfies our condition from beginning. If it satisfies the condition, then we can just put lambda equal to 0, and we have a least squares. Yes. The problem starts when it doesn't satisfy this condition here. Then we have to modify it. So when we modify it, then we will get this general question here, or estimated here, but we have to estimate lambda. And lambda is estimated from this relation here, from this equality. And this we cannot solve explicitly if you don't have very, very special design matrices C. But it's still, we can manipulate a bit. It's just a one-dimensional equation. Lambda is a scalar. So one can find a solution. The problem is, of course, we don't know properties. We just use an algorithm here. Well, I haven't tried. Maybe one can do some expansions and things. I haven't tried this. And in ridge regression, because they don't have the t there usually, when you penalize your estimation function, then they have some other criteria how to choose this lambda. And they can think about minimizing some kind of empirical mean square error, or using cross-validation to achieve some results according to some criteria, and then they find an estimate. But it's even more difficult than to really evaluate it. But the point here is that if we have put our T realistic in some way, we have so much information, and then the data which we have observed or got makes that this relation is fulfilled, then we should just use ordinary least squares. We should not try to improve anything. And I think this is forgotten when we talk about all this penalizing function, because they penalize automatically. And I can imagine that it's just too much sometimes, depending on the problems, of course. But people are not thinking today. They just set up they have some data set, they put some general complicated model, and then you penalize things, and then you get the result. But here it shows that you have an alternative. The old classical results work very well. And of course, there is a game, how should we choose T? And this is like a priori information. How much do we know about our processes? And of course, we can start to cheat. If we want to have a large T compared to our data, we will always be safe. So there is research which should be done how to use this type of knowledge in a good way. And it depends obviously on your C matrix. If you have many objects with different scales, how should you proceed them? Because when you sum together all these elements, or you have different size of effects, then of course some will be dominating. And when you square them and put them together, it's mostly about one effect. And this is of course not good. But this is an open question, at least for me, how to use this information in a good way.
So can you elaborate your open question?
Sorry?
So what is your open question here? So what is your open question here?
No, it's to choose T.
How to
choose
T?
Yes, I can, if I know study growth, for example. I know that the child will not grow more than 15 centimeters, something like that, the first year. And then you come into teenage spurt or whatever. This type of condition I would like to put on the beta.
How about on the beta itself? Is there some kind of a thing which you have a knowledge about each individual beta?
I have, as usual, I have knowledge about the beta. I expect something from my experiment.
Yeah.
So which, if something completely crazy comes up, I would just, I wouldn't trust the experiment.
Okay.
So if I study hormones, for example, I have pretty good knowledge what the level of the hormones should be and what the effect should be for say, melatonin, cortisol, or whatever you put. So this type of knowledge I want to.
No, what I'm saying is individual beta coordinates. You may not be, of course, we don't know how to estimate whatever it is. I am saying beta 1, beta 2, beta k, whatever is the.
Yeah.
Probably they are caught in areas, intervals on which you have some knowledge.
Yes.
If that is the case, that gives an estimate for T.
Yes, but the problem, I agree.
Yeah.
You have it, but since you are summing there, if you have too many background, this sum can be pretty large, maybe.
Yeah.
And maybe it
No, I'm not
becomes
summing, you're
under that.
squaring them.
What?
You're squaring each one of them.
Yeah.
So, and that gives you a bound, and that T, to get your T, rough T.
Yes, no, of course I can get it, I can imagine, I can combine it like you're saying. This is not the problem, but it's still, if you have many variables, you don't know really.
Which one is important?
Some are maybe more unreliable than others.
Yeah, I see.
And so in that sense, this T is can be difficult to put. Maybe one puts it too high also. If you have many variables, if you think that there's a random, because then not all should be on the top. Maybe some will be high for by chance, and then some others is lower. So that could also be something which can be studied. But I'm not doing this now. I just suppose I have this T here. Okay, so what we for fun, one morning I asked us, what shall you can put a name on this regression, what I'm producing with two two alternatives. So I call it safety belt regression. I don't know. That if you have bad observations or something bad, then we put on our penalized estimate. So this would be our safety belt. Otherwise, if our observations are in a good, appropriate in relation to T, we just use the usual procedure. And doing that, we have simulated a bit, and you see that the idea works pretty well, in fact. Okay, this is the history. I will not. Yeah, these last ones. Now you can modify this a little bit also immediately. You put just a semi-definite matrix here in between, just to pick out, for example, elements. But you can also put in, like you saw CC transpose. You can use CC transpose here and minimize, and then you come up to the so-called James Stein estimator. Otherwise, this is maybe most natural. So if you have a regression, you know pretty well about the slope, but the intercept, you will not put any restriction on. This is a typical example. Yeah, he's just with his age. But then we come up, now it was least squares, but then when we have, oh, pardon. You can spend the whole day here. No, but I will show you about the likelihood. And then usually assume normality. The advantage with this that we can treat both the variance and the mean parameters simultaneously. So in this case, when we have a univariate normal distribution, this is the same setup as before. Then it's not so complicated because we look at the negative log likelihood function. This is, we don't even think about convexity. We can immediately find an upper bound for sigma square here. And that is given here as an inequality. And then here we have the least squares criteria. Aha. I don't have so long arm. So, thank you. So you have the least squares criteria, and this is a monotone function. So he will leave the convexity because this function here, the logarithm of this function, when you parameterize it with beta, it's not convex. But the least square function here is convex. And then we know that this inequality which we had here, that always, when we take a beta here, it always have this relation here. Well known fact. So what we have to do is just go back then to least squares and find an estimate of beta. And once we have this estimate of beta, we have an estimate of sigma square also. So and this is what's going on here. We have the KKT conditions and we solve them. But I will just very quickly go to the normal case, what we're doing, or multivariate case. So suppose we have a p-dimensional normal. We have a p-dimension, this is a matrix here, mu, or there should be a design, sorry. Or no, we have it like this, then it's okay. But when we know this model here, or a situation, then we have is or convex. So we have two canonical parameters. One is related to the mean, but if you can see a mu, you have sigma inverse here. And so one can discuss why this should be there as a canonical parameter. And then we have a lower triangular of a symmetric covariance matrix, or de facto inverse. These should be canonical parameters here. For the growth curve, it looks, then we don't have really canonical parameters, so we have to do something else. But here we are now. And then the idea is that this will give us some kind of convex optimization problem, estimated zeta 1 and zeta 2, and then we go back to the original parameters, because this is so this is a procedure, and we should see what happened here. He is really the man of our model. We have the same design matrix as before. It just we have p-dimensional vector. We have a matrix here, and then we do the same. But now we have in the canonical parameters, we have a likelihood of this form. And here we can see that it will, if you differentiate it twice, and we have this is a convex function. Same if you look at the restrictions, which we have. I didn't tell you the restrictions here. Restrictions are given here now. And the reason I include sigma inverse here is just that I want to have a convex optimization problem. And in the univariate case, I just remove the sigma. We could have it as a trace b beta. But in the multivariate case, we cannot do it. A bit an open question how to do, but we maybe should learn to handle this type of restrictions also. So, and then we can translate these restrictions into the canonical parameter.
Capital sigma inverse b beta is complex. It's straightforward.
Here we have, this is a convex function. It's a negative log likelihood.
Okay.
And that is convex.
Okay.
Because you can differentiate. You can differentiate the determinant. And I said I could talk about technical things more. It's how to use matrix differentiation of a symmetric matrix here, or the determinant. And then you see this restriction here is the same form as here also. So this is really convex.
No, you said that you have to multiply by sigma inverse to make something for the convex condition.
So
No.
well,
You said that we should multiply sigma inverse,
yes.
and that is the thing which helps in some sense to address the sigma inverse b beta. Yeah. What is it which it does? It makes.
If you don't do it, you will get, because we want to express our function as a function of the canonical parameters.
Okay.
And then we use the canonical parameters inside here, and that will not be convex anymore. So because we still, if the convex, you had sigma inverse b here,
yeah.
So you should have another sigma inverse here, then, and then you will see that it will not be convex.
Okay.
And so that is a problem. Yeah. So this we can handle here, and I will not.
So this is available in that book, convex optimal?
No, they don't do it. These are, I don't know, not numerical people, theoretical, I don't know, computer science. No, I don't know, mathematicians maybe. It's a good book. One can learn a lot from it, and I just used it when I can use the KKT conditions. So one solves it. I will not tell you what this DP are, but it's a more Penrose inverse of some DP they call it duplication matrix. Here is his solutions if you go back to the original parameters, and they remind pretty much what is going on in the univariate case. So it's just this covariance. You have a term 2 here, whereas outside is 1. If usually we would have just the lambda, and then it would remind very much about the univariate case. And then then lambda should be found from such an equation, which is a problem, of course, a bit. It's not trivial, I would say. I will stop now. Later, I will should have talked growth command about this here, but this will take next time. So, thank you very much for your attention.
Are there any questions at this time? So it is a nice talk, and I'm interested to look into more details. Perhaps that I'll take the slides from you and go through more details.
I can send, we have a manuscript in preparation, with some courses.
Okay.
And soon we have submitted it, then I can send you it. And I don't dare to.
Okay. So it's really interesting. In
The
fact,
basic thing is you are connecting optimization with statistics. And that's a real way by which the students can get into. See, students know one of them and they don't know the other one.
exactly
That's how we think.
at ISI, when I teach
ISI
cross-cultural condition, so this will be a nice thing to connect those statistics students.
Yes.
So when you teach cross-cultural condition, so this will be a nice illustration to connect statistics and this to know that so that they will be motivated to know more.
I think so too.
Yeah, so it's a nice way of saying so that it will be really beneficial for the statistics student.
Yeah.
So they will know other approaches in the optimization. Perhaps we can motivate them to learn optimization more.
I think so, because there's so much, this convexity is restricted. So if you can start to use it like local convexity and use that as a tool, you can improve things. I'm sure.
And your trick, no, that capital sigma inverse, and so that trick is really nice, no, that so how you convert it into a convex one and then go about it.
So this is the first time I am seeing both being connected.
Yes, I also feel so.
Yeah.
I wonder if we could move this conversation to our position. We've been running out of time. So, thank you, Diedrich.
Yeah, thank you.
So as a token of our appreciation, I request Professor Hasselwood to hand over the memento to Professor Rosen.
Thank you. Thank you.
Thank you, Professor Rosen.
So more.
Well, I'm very sorry to cut the conversation short on the end of the last talk. I think these conversations are probably at least as important as the talk. So please, I hope you can continue at lunch. Our next speaker is Dr. Sudhir Bhatt from the Indian Institute of Management in India, of course. But he's also he's currently working as visiting assistant professor at the Department of Statistics and Applied Probability at the University of California in Santa Barbara. I think the interesting thing in the conversation we had earlier was your statistics was linked particularly to sequential analysis, and the other, you're working in a management area.
Yeah.
The links between these two are very interesting, while it's not quite the topic of your talk. So
Thanks.
thank you very much.
Yeah, sure. Yeah, so firstly, I thank Stephen for the warm introduction. And then again, it's always nice to be in the southern part of India. So I think this is the southernmost point of the India I've traveled to yet. So I've been to Bangalore before, but not to Chennai and all those places. Especially food and all. So the last couple of days we have dosas and all. So it's kind of nice that way. Anyway, so I think this talk would be slightly different flavor. I mean, it'll be more of statistics in nature. And then this is more like a connection between some reliability example and then my PhD thesis, which was in sequential. So as he mentioned, it's always a nice thing to have a connection between some data analysis these days with some application, and then a bit of a theory also there. Okay. So the title is slightly long, so it says maximum precision estimation for a particular kind of a model, which is called a step stress. And then using some sequential ideas. The last thing that you see there is just two-stage methods. So especially two-stage methodologies, it's a very core kind of a idea in sequential. Okay? So I'll try to elaborate all these points and then how the connection could be made with a small application. All right, so a bit of an outline, and then down the line we'll focus more on some real data, which is more pseudo-real data. So getting some actual application, let's say some big data, is not quite possible, because I try to explain as the entire idea of sequential is more to kind of save some time and then also cost, right? And some of the key applications in sequential estimation may be, let's say, in public health, or let's say ecological based data sets, where one has to go to the field and then collect the actual data set. So let's say if you count the number of insects, it's a very simple example. But sequential idea means that you can collect the sample sequentially in, let's say, some batches, or let's say one at a time, and then hence try to save some time on that and cost, right? Yes, and then the fifth point you see here is the actual idea, which is two-stage formulation. And then we'll give a brief literature review also. So since this entire topic would be new for many of you, so we'll try to link this to some application later. Right? And then what exactly is the problem? So the highlight of talk is to, like I said, make the connection between that two-stage sequential strategy. And then here we have this one particular idea in reliability called as accelerated testing. So how can you make the connection between two-stage and accelerated testing using, so under some cumulative exposure model. So we'll try to elaborate on that. Yeah, and then even inside that accelerated testing scenario, we'll focus more on step stress methods. So a particular kind of accelerated testing scenario, which is called a step stress. All right. And then just to mention that last point is that we'll assume that the stress level, so let's say you have a particular device, right? And then let's say which fails sometime in between. So once the device fails, you have to change the stress level after that. So using some sequential ideas, we'll try to find out as to exactly at what point one should change that stress level, right? So stress level happens to be random here, and it can be of either type. So let's say after a fixed number of failures occur, or after some time has passed, right? Okay, so the underlying idea is nothing but to estimate the parameters. So let's say you put some distributions on both the sets, so before the failure and after the failure. And then the real problem here is to kind of estimate the underlying parameters under both the situations, right? It could be a very complicated kind of a structure where you have some mixture distributions at both ends, and then let's say how to estimate the underlying thetas. So even if you take some simple exponential distribution on both the failures, but yet in the literature, it's not very extensive yet as to how should one estimate the parameters under both the stress levels. And then down the line, the fourth point you see is more like you have to ensure some maximum precision. So maximum precision could be of multiple types. So here we'll focus more on, let's say, maximum precision would be, let's say, to minimize the variance. So it's called a variance optimizing criteria. So one can either do it using some bound, let's say some upper bound on some risk or something like that. So let's say, and then that idea is called as bounded risk problem. And then on the other hand, you have a minimum risk problem. So this problem falls under the minimum risk because you want to minimize the variance of the overall structure. Okay. So a small background. So I thought of adding this again, just to repeat, as to probably many of you be kind of new to this entire idea of, let's say, censoring and all that. And then the broad topic is called lifetime data analysis. And then let's say which is mainly to focus on the time until the event occurs, right? So if you want to, let's say, estimate the underlying parameters, and then let's say time until some major event is occurring, and how to estimate that underlying parameters of the distribution. And then here are some general examples where, let's say, time until some tumor recurrence, or let's say time until some cardiovascular death after some treatment intervention, right? And so on and so forth. And then the fourth one mainly comes from a reliability angle. So let's say time until a machine part fails or something like that. And on the other hand, so the next idea, which is censoring idea. So again, censoring idea is kind of very widely applicable even in these days. And then broadly speaking, this slide is more of an introduction to that. So you do have like two different kinds of censorings. So it could be the right or left. I mean, of course, you have other types, but then right and left are kind of the more predominant ones. And the right and left censoring schemes, they kind of differ into as to at what end you have the missing observation, the missing link, basically. So we'll try to discuss some examples very soon. And then even under the right censoring, so this is a small definition of right censoring. So let's say you have some subjects in a clinical trial, right? And then, so right censoring would occur if, let's say, some subject leaves the study in between, right? So even before the end of the study, the subject leaves the study, then that observation would be basically right censored in a way. Or the other option is if the study is terminated before the event occurs, right? So let's say the organization decides to stop the study entirely. So these are the two kinds of right censoring mechanisms which are kind of slightly more applicable in nature. And then again, even inside the right censoring scheme, you have two different kinds of right censoring. So let's say type 1 and type 2, which are famously known. And then type 1 right censoring occurs if the study ends at a fixed time. So let's say you fix some time, so let's say probably 10 days, or let's say 1 month, and then you have to end the study right there, regardless of the fact that how many observations or how many failures you observe, right? Or on the other hand, you have type 2 right censoring. So let's say you observe some failures, let's say 100 failures or 200 failures, and then after observing those many failures, you stop the study. Right? So, so just to repeat, so type 1, you have to fix the time point, so let's say 1 month or something like that, and then type 2 censoring would be you have to fix the number of failures you want to count for, right? And then on the other hand, left censoring, so as compared to right censoring, left censoring is slightly lesser applicable in nature, and you get some, I mean, you do have applications there, but then people these days, I mean, they work extensively on right censoring, especially. So left censoring occurs if the event of interest occurs before the subject enters the study, right? So a small example here is, let's say your job is, so you get up one morning, and then your job is to, let's say, find out. So you go outside your room, and then you have a tree there, right? And then you have to find out the exact time as to a few birds are sitting on the tree. So you have to find out the time as to when they arrive, right? So the moment you go outside, you see some of the birds are already there. So those observations are left censored because for those birds, you won't be able to find out the time they came and then sat on the tree, right? So here's a small example of left censoring. And right censoring, you get a lot of other applications. We'll discuss a few here also. Okay? Yeah, I think this slide would be kind of beneficial because it's more like a pictorial slide. So let's say you have 5 participants. So 1, 2, 3, 4, 5. And we have these 2 vertical lines which are start of the study and then end of the study, right? And then especially, so a small diagram as to what each notation means. So let's say so the red crosses means the event has occurred, basically. So if you see, the first one is kind of not censored because the observation was there before the end of the study, right? So the practitioners were able to find out the exact observation before the study ended. But if you see the second one is right censored, of course, because the observation occurred after the end of the study. So the red cross after the second vertical line. And then this green arrow you see is stayed. So let's say if you have some patient who stayed in the study and an event has not occurred, right? So still we'll say that the observation is right censored because you don't get the failure time for that patient, right? So this way, it slightly differs as to whether the patient is staying and then kind of continuing the participation in the study, or the study has ended, right? And then after the study ended, the event occurred sometime. So right censoring could be of such multiple types. But if you focus on this fourth one, so fourth one is kind of left censored because you don't know the start. I mean, even before the start of the study is unknown for that patient. So you see a dashed line there, right? So you don't know the time as to when exactly the study started. But then of course it's not right censored because the event occurred before the end of the study, right? And the last one is kind of interesting, so it's slightly different. It's called as interval censoring. So interval censoring means that if you don't observe a portion in between, right? And then let's say, so you have a missing link here, right? And let's say, so inside that missing link, if the event occurs, then you won't know the exact time for that, basically, right? So it's kind of a mixture of left censoring and right censoring. So if you have some missing link in between, right? And then one of my other papers was in similar lines called middle censoring. So, so middle censoring is kind of similar to interval censoring. So a small example here in the last case could be, let's say, so all of you must know that you give some stars for Amazon ratings, right? And then let's say, so generally what people do is they give 1 star, 2 star, up to 5 stars. But if you create a slightly different problem where you try to rate the products, and then those stars could be in the form of intervals. So let's say anything between 2 stars and 4 stars, or something like anything between 1 star and 5 stars, right? And then this could be easily modeled using some multinomial problem. So you have to estimate the parameters of that multinomial problem. The only thing is that if you have, let's say, between 2 stars and 4 stars, then some contribution comes from 2 stars and some contribution is there from 4 stars. So you have to actually mix and match both the possibilities there, right? Oh, yeah. So one major problem. So again, if you go back to the diagram, is that so wherever you see right censoring, right? I mean, right censoring means that the study has ended, and then you don't observe any failures there before the study ends, right? So in that case, it's kind of not very advantageous because you don't know the time at which the event has occurred in right censoring. And for this very reason, we use accelerated testing, right? So accelerated testing means that you kind of increase the stress level slightly to induce more number of failures, right? So let's say if you're not getting enough failures, so if you have a very handful of sample observations, then probably you won't be able to estimate the parameters, right? But let's say if you induce some slightly higher stress level, then probably you might induce some earlier failures, right, than required. So so there's a small idea where so accelerated testing could be one solution where you kind of put some higher stress levels to achieve early failures in that sense, right? And then last line, I kind of discussed a short while back that the time point. So let's say you want to change the stress level at some fixed time points, right? So you have to actually find out exactly at what time should you change those stress levels, right? So all those time points would be kind of random as to when you change the stress levels to a slightly higher stress level and so on, right? Yeah, so this small example again. So let's say, so all the components are subject to varying stress levels to induce quicker failures. So this is the main idea in connection to all that. So again, a small example could be, let's say you have a light bulb manufacturer who wants to observe the number of failures in 10 years, right? And then assume that the mean lifetime of all the bulbs is 30 years, right? So in this case, probably he won't be able to get those many number of failures, right? So probably in that case, what he can do is he can put some bulb in a slightly higher stress level. And then in this case, probably a higher stress level could mean higher voltage, right? Or something like that, or maybe higher temperature or something, such that he or she is able to observe much more number of failures as required. Okay. And then ALT is a short form of accelerated testing, is used on a reduced load to see how much the component life will be extended in this case. All right, so if you focus more on this accelerated testing scenario, you have these two kinds of stress profiles. So we call these as stress profiles in literature. So on one hand, you can see that you have constant stress profiles. And then such a thing could be kind of useful when you have a lot of data at hand, right? And then such a thing may not be useful if you have a very small number of observations, right? And then what you're doing here in the left diagram is that, let's say you divide the entire number of observations into equal parts, and then you put each part or each subdivision at different stress levels, and then all those stress levels are constant, right? So let's say this is the lowest stress level, so you put one batch there, and then you might want to put another batch on a different stress level, and so on. So from each batch, you're able to find out the failures in that sense. But on the other hand, what we call is a step stress profile. So step stress means you put the entire batch on one stress level, right? And then probably sometime in between, you change the stress level to a higher level. And then again, you change the stress level to one more level and so on. So it's more like a step, right? So you have all the observations put on stress level 1. And then sometime in between, whenever you feel, you kind of change the stress level to a slightly different one. So it forms a step, right? So again, in this work, we'll focus more on the right side because again, sequential idea, like I said, is more applicable when you don't have a lot of observations, right? So let's say if you only have 30 or 40 and so on and so forth. But on the other hand, if you have many observations, then probably you can focus more on the left side, right? All right. Yeah, but again, you have some, so you have pros and cons with each method. So these are some cons of the ALT technique. That kind of estimation becomes rather difficult here because let's say you're changing the stress levels and then you have to actually monitor the estimations at each level, right, down the line. And then in this way, it creates a mixture kind of a distribution. So you won't get, let's say, a constant exponential throughout or something. Because you may imagine that once you change the stress level, the parameters would change, right? And then if you want a joint distribution to model the entire stress, what do you call it, stress factor, then it's kind of not very easy. Okay. So the model becomes more complex. And then even in simple case, analysis becomes difficult. So let's say if you want to estimate the parameters, so probably a simple MLE won't do the job. So it requires some profile likelihood technique or something like that. Yeah. Okay. All right, so again, just one last slide probably on what exactly do you mean by step stress. So I think we mentioned a number of times, but just to give a recap is that, so let's say you observe the failure times of the objects at particular stress level, then again you change the stress level to a different level, and then observe the failure times at the new stress level, and so on and so forth. Okay, so again, if you go back just for a second to this graph, so we'll focus on this kind of structure, where let's say if you have smaller number of observations, so you can put all of them at one stress level and then keep on changing down the line. All right, and then again, we can bring in the idea of censoring here. So it's not a difficult task here. So let's say the idea of right censoring under type 1 or type 2 schemes and so on. So even under ALT, it may happen that even if you change the stress level, you won't see any failures, right? So again, that problem is a censoring problem. Right? But at least we can ensure that the failures you would have observed if you did not induce the step stress idea. So under a step stress idea, the number of failures would be certainly more, right? Because according to your desire, you can actually change the stress levels at fixed time points or after also, let's say, a number of failures you see, right? So again, the problem can boil down to, let's say, either type 1 censoring scheme or let's say type 2 censoring scheme again, right? Yeah, so the problem formulation is kind of not very difficult to understand. So let's say you have n items, right? And then one simple example you can take in your mind is, let's say, light bulb example. So it's a very common technique to start things with. So let's say if you have n light bulbs which are put on some stress level, let's say x1, right? And then after you observe n1 failures, right? After you observe n1 failures, you have to change the stress level, right? And just not to complicate things here, we'll keep it simple. So we'll only focus on 2 stress levels. So let's say x1 and x2, right? So sometime in between, you make one change and then try to estimate the parameters underlying both the levels, right? So initially, let's say again, just to recap, you have n in the beginning at a stress level x1, and after you observe n1 failures, you change the level. You change the level to, let's say, a different stress level x2. And when do you stop the experiment? So you stop the experiment after you observe R failures. And here R would be nothing but the sum of N1 and N2, right? So N1 failures coming from the first stress level and then N2 coming from the second stress level, right? So this is a simple problem. And then we can also assume that the distribution at both the ends or for both the partial distributions are again exponential. And again, so even though the distribution is exponential, the problem is not very easy, as we mentioned earlier, because you have to make that connection between the 2 stress levels also, right? So it's the problem is not as simple as, let's say, estimating thetas under both the levels separately, right? But nevertheless, so let's say if you assume that they're kind of exponential with those means, so 1 by theta 1 and 1 by theta 2, and then here we can kind of assume that the overall model is the cumulative exposure model, right? Which was kind of analyzed by Zhu et al. In 2019, right? And then this cumulative exposure model kind of connects both the exponential distributions to give a kind of a complete structure in that sense, right? Okay, and then this is exactly the model. So here, if you focus on gamma, right? So gamma is some random point at which you will make that change, right? So obviously before gamma, you would only have the impact of the first exponential with mean 1 by theta 1. And then after gamma, you would have the impact of both the parameters, theta 1 and theta 2. So whenever the random change point exceeds gamma, then you have the effect of both the parameters theta 1, theta 2. But as far as the time does not exceed gamma, you only have theta 1 into play because only a single distribution is there, right? Yeah, and then again, so it turns out that one can actually get the MLEs kind of easily here because the structure is not very difficult. I mean, the only thing is that you have some random point in between, which is gamma. So you can split it into two halves and then try to find out the MLEs. So it turns out that the MLEs of both the parameters are actually N1 by T1, capital T1, and then N2 by capital T2, where both T1 and T2 are as follows, right? And then here we have to actually introduce the idea of order statistics because so you can actually observe the failures in some order, right? So let's say TIN is the lifetime of the ith item which fails, right? So again, if you remember after what point do we change the stress level is after N1 failures, right? So we'll focus more on this guy. So TN1 colon N. So TN1 colon N is the lifetime of the N1th item which fails. Okay. So these are the MLEs for both the parameters along with their complete sufficient statistics. So T1 and T2 and so on. Yeah, so now the link between this entire reliability exercise and sequential is exactly what. So again, just to recap, so the time point after you make the change is also random, as we discussed, right? So so you have to actually find out as to when exactly should you make that change, right? So that time point is kind of random. And then here, it so turns out that a fixed sample solution does not do the job. So you do require some sequential idea. So again, just to recap very quickly, a sequential idea is you keep on taking or you keep on collecting data one after the other in some sequence, and then it has to meet some stopping criteria, right? And the moment it stops, the entire process stops. So you actually retain or you try to estimate the parameters using those many observations which you have once the stopping rule is met, right? So this is a broad idea about sequential. And then why sequential here? Because we have to actually ensure that variance optimal criteria also. So we don't want to just estimate the parameters, but on top of that, we have to ensure that the variance of the estimators are kind of minimum, right? So you're kind of controlling two things here. You want to estimate the parameters and try to minimize the variance, right? Which can't be done using a fixed sample solution. All right, so how exactly would you adopt the variance optimality criteria? So by the way, this expression which you see is the total variance of both the estimators. I mean, of course, not the estimators, but the population variance. So you see theta 1, theta 2, and all the other notations we've seen so far. So R, N1, etc. And then you have to actually minimize this variance, right? So you have to minimize that variance and try to estimate the parameters, the underlying parameters. So here we'll adopt something which is called as two-stage criteria. So two-stage criteria is one of the very basic sequential criteria. And then two-stage means that you have to collect the observations in two stages. So you have the first batch and then you have the second batch, right? So firstly, one can do a very simple exercise. And then if you want to minimize this variance, then try to find out as to what n would you require, right? So differentiate that, set it equal to 0, then find out n1 in this case, by the way. And then so it turns out that the n1 happens to be that guy. So theta 2r divided by theta 1 plus theta 2, right? And then that n1 is called as the optimum n1 because at that n1, your variance would be minimum, right? And then using some two-stage criteria, we'll be able to estimate the parameters also down the line. Okay. And then again, at that N1, this is the minimum variance of the entire structure. Right. But here you clearly see that this variance is kind of unknown because the parameters are unknown. So both the thetas are unknown. So we have to resort to some sequential strategy here. So how do you estimate the thetas? Yeah, so a very brief background, I think, of sequential procedures. So I think sequential procedures goes back to probably 1940, and then probably in all the textbooks you see SPRT. So SPRT is the sequential probability ratio test. So we test some hypotheses and so on and so forth. Right, but then again, down the line, you have all these extensions. So let's say minimum risk point estimation or bounded risk point estimation. Right, so all these are kind of extensions of sequential idea under point estimation strategies. Right, and then two-stage was kind of introduced by Stein back in 1945. And then again, on top of two-stage, you're purely sequential. So purely sequential means rather than two batches, you collect the observations one at a time. Right. So let's say you collect some pilot sample, and then you collect one observation at a time until the stopping rule is not met. Okay. And then you have a combination of two-stage and sequential, which is called accelerated sequential. So you collect observations in some batches initially, and then once you meet some criteria, then you adopt the sequential strategy. So all these are kind of extensions of exactly how should one collect the observations. So should they be in batches or one by one, and so on and so forth. Right. Yeah, and then of course sequential can be applied in other areas also. So let's say selection and ranking problem. So if you have two normal populations, so how would you rank the means? So let's say you want to find out whether mu1 exceeds mu2 or mu2 exceeds mu1, right? And then one can actually do this using a sequential idea. So let's say collect just a handful of observations, and then until the stopping rule is not met, you keep on collecting more observations. And once the stopping rule is met, then you actually make use of only those number of observations to find out exactly as to what parameter exceeds the other one. Okay. All right. So again, just a quick recap of two states. So in all the sequential ideas, we would actually collect a pilot sample because so one can't start estimating the parameters without any data, right? So you have to actually collect a small sample. So the first line is collect a pilot sample of size m, and then that's m is kind of very short. So let's say 5 or 10 or something like that. So even if you have an application of ecology, so let's say a simple example could be, let's say, count the number of insects in a field, right? So one can always go to the field and then collect the pilot data. So pilot data is not so that m is a small number, like I said, so 5 or 10 or something. And then based on that pilot data, you try to estimate that, you perform that initial estimation. Okay. So estimate the parameters based on this pilot sample, and then design a stopping rule. So you have to design a stopping rule based on those estimators, run the stopping rule, and then the moment the stopping rule stops, it gives us the final capital N. And then that capital N is the ultimate sample size. Okay. And then again, since we're adopting a two-stage rule, so if capital N exceeds M, so M is the pilot sample size, then you move ahead and collect the remainder number of observations, which are nothing but N minus M. And if capital N does not exceed M, then your overall sample size is still N, basically. Okay. So two-stage means nothing but the two batches are what exactly? So the first batch consists of M, number of samples, and then the second batch consists of the remainder if required. And then that remainder is nothing but capital N minus M, right? So overall, one has to stop after capital N number of observations. Yeah, right? Yeah, and then on the other hand, you have a purely sequential procedure. So in this work, we'll not focus on that. But then what exactly is purely sequential? So again, you have to collect a pilot sample of size M, and then again estimate the parameters based on that pilot sample. The only difference here is that you design a stopping rule based on the estimators, but until the stopping rule is not met, you keep on collecting one extra observation at every time, right? So this is the only difference between purely sequential and two-stage, basically, right? So rather than collecting data in two batches, you're doing that one by one until that stopping rule is not met. Yeah, and then probably I'll just focus on what exactly is capital N in this context, right? So by the way, this is capital N. So if you see capital N, it comes out to be that expression, right? So maximum of M and then some expression involving estimators. So all these are the estimators now. So theta hat, theta 1 hat, theta 2 hat, etc. Now the whole idea is that if you remember the exercise, so what we're doing is let's say light bulb example. So you collect one batch of light bulbs, right, and then try to find out the estimators, right? But how would you be able to find out theta 2 hat? Because theta 2 hat, if you remember what exactly is theta 2 hat, so theta 2 hat is nothing but once you change the stress level, what exactly is the parameter, right? So if you don't change the stress level, how would you obtain theta 2 hat, right? Because theta 2 hat is the after parameter, right? And then before parameter is theta 1, which is okay. So theta 1 had to be found out using pilot data, right? But until you don't change the stress level, you won't get theta 2 hat. So here we adopt a simple strategy. So let's say if you have n light bulbs, you can divide them into equal halves, n by 2 each, right? And from the first batch, you can actually obtain both the estimators, right? Theta 1 hat, theta 2 hat alone. And once you obtain those, you apply them on the other batch, right? So, so this way, let's say a simple example is that if you start with 100 bulbs, you divide them into two halves, 50 each, and then use the first 50 as training data. So you can use this as training data, testing data kind of a scenario, right? So use the first 50 as training data, find out the estimators, and then using those estimators, find out capital N, right? And once you have capital N, you exactly know as to after how many failures you should change the stress level. So then you can adopt this strategy on the other 50, right? Or for that matter, once you know capital N, you can apply that on any similar batch which comes in the future, right? So the only number of light bulbs you want to exhaust here are nothing but the initial 50, right? And afterwards, I mean, assuming that you get light bulbs from the same company and so on and so forth, all the light bulbs will be kind of similar. So once you get capital N, you can you exactly know as to after how many light bulbs have failed, should you change the stress level to a slightly different level, right? Yeah, so there's a small tweak here, since you have to actually find out both the estimators and exactly why, right? Yeah, but again, once you find out this capital N, then the problem is easy. So using this capital N or capital N1 in this case, then you can actually find out the final estimator. So theta 1 based on capital N1 and theta 2 hat based on capital N1, right? And then these are the estimators. So these are the final estimators, and the final number of observations you should collect overall are nothing but capital N1. And then these are some general convergence properties we kind of prove in any sequential idea. So you, on one hand, your first order, so let's say N1 by N1 star goes to 1 with probability 1, and then expected value of N1 by N1 star also converges to 1. So all these are kind of standard properties which any N1 should satisfy, basically. And then on the other hand, your risk efficiency. So if you remember, once you look at the capital N1, you have to find out the variance also, right? So it's always better if the estimated variance and the population variance, the ratio of those converges to 1, okay, which is given by nothing but risk efficiency. All right. So these two are the famous properties which one should always look to proving if you're kind of proposing some sequential idea, right? Yeah. So probably it's a very big table, but then probably I'll just explain one row really quickly. So all these are simulated data, right? So let's say you simulate. So firstly, what you assume is you can assume some parameter values. So let's say theta 1 is 0.2, and then theta 2 is 0.1. And then all these results come from 10,000 replications, which is a standard number in statistics. So let's say the first column gives you n. So if you remember what n is, so n is the overall number of observations. Then what exactly is small n? So m is a pilot sample, right? And then r is after how many failures should you stop, right? So if you look at this highlighted row, so let's say 300. So 300 should be the overall number of samples, or the overall light bulbs you have, right? And then R being 100 means that one should actually stop after 100 failures, right? And then from that you can see that, so if you compare these two columns, so N1 star and then NT bar, they have to be close, right? Because one is the estimator of the other. And you can see here that both are roughly 33.33, right? So NT bar should estimate N1 star. So N1 star is unknown. yeah, so N1 star is unknown, and then NT bar is used to estimate N1 star. Okay. Okay. And then the first order approximation is also satisfied. So if you take the ratio, so NT bar divided by N1 star, that should converge to 1, which you can see there. Right, and then the important thing is that the estimator should be close to the true values, which is happening here. So theta 1 hat bar from 10,000 replications on an average should converge to 0.2, which is the true value. And then similarly, theta 2 hat bar should converge to 0.1. Right. So this is the initial table, and then the next table is in the form of variance optimality. So if you look at this column, right? So this is nothing but the risk efficiency we discussed a short while back. So all the numbers there should converge to 1, which is happening here, right? So in this paper, we haven't proved second order approximations. Second order means we take a difference. So something like tau 1 hat bar minus tau 1 N1 star, right? And then that value should actually be close to 0, right? But in this paper, we're kind of left proving that second order approximation. But again, like I said, these are some standard properties that one proves under sequential idea. And then, yeah, so pseudo real data analysis. So this was a very small data set we found out. So one by Xiong and Millikan in 2002. Right. So again, like I mentioned, that getting some actual data and then the sample number is also large is kind of difficult. Because this is a reliability example, right? So reliability, you require those many failures to observe, right? But nevertheless, so there's a small, so I think the sample size here was kind of 20 or 25. So we kind of extended that. So extended means that you take the real data and then try to simulate some similar looking observations from that real data, right? So this is not exactly a real data, it's kind of pseudo real, right? So small cheating kind of a thing, right? Anyways, but then again, the idea is exactly same. So, and then we try to estimate both the parameters. So let's say 2.5 and 1.5. And then in their paper, that mentioned that the distributions actually follow the cumulative exposure model. So we could actually use that directly, right? So let's say the first exponential parameter happens to be 2.5, or rather the estimator of that. And then the second estimator happens to be 1.5, right? And then what we did was we kind of extended that to, let's say, 100 observations, right? And again, kind of a similar technique. So you start with 100, and then you fix some R. So again, R means that when should you stop the experiment? So let's say once I observe 30 failures, I'll stop it right here. Okay. And then N is the pilot sample. So again, N happens to be 5, which is kind of a small number, usual one, right? And then again, let's say, so in this case, the parameters happen to be these, right? Because you have to take 1 by theta 1. So 1 by theta 1 happens to be, so yeah, so by the way, these are the means, right? So these are the means, which is 1 by theta 1, 1 by theta 2. So you invert them to find out the parameters. So 0.67 for the first exponential, and similarly 1 by 2.5 for the other, right? So these would be the theta values. And again, like I said, so let's say you split 100 into 2 parts. And then you utilize the first part to kind of estimate the parameters, right? And once you estimate the parameters, you find out capital N or capital N1, which is the stopping variable. And then in this case, it comes out, so stopping variable comes out to be 19. So what exactly you mean by that is, let's say, so the moment you observe 19 failures, you make the change, or you change this stress level to a different level, right? So the moment you observe 19 failures, you change the stress level to a different level. And again, so then you stop the experiment after you observe 30 failures, right? Because R is fixed here, so R is 30. And for this real data, I'll show you the table. So these are the failure times or the lifetime. So the first batch, we count them, happens to be 19. And after 19, you change the stress level to X2. And all these are slightly different failure observations or lifetimes, basically. Okay. And again, you have to kind of ensure that all the properties are met. So once you get this final data, you again try to prove that first order efficiency and then risk efficiency and so on and so forth. And then the property should be kind of met again. Right? Yeah, so the conclusion is just that, I mean, there's a small connection between reliability and sequential, right? And then especially step stress. So step stress, and then we've kept the change point to be random. So one does not know as to exactly when should you change the stress level, which can be actually found out using a sequential idea. All right. And then so such a structure is not possible in a fixed sample setup, as we discussed before. All right. And then some future ideas could be, so I'll give you just one or two. So apart from looking at two-stage, one can actually elaborate and then extend to purely sequential also, right? And then a similar idea can be applied to other censoring schemes also. So so you should not, if you don't want to focus only on, let's say, type 1 right censoring or type 2 right censoring. So one can try to look for some similar analysis in, let's say, middle censoring or left censoring, and so on. Okay. Yeah, and then these are the primary references as to exactly where that step stress model was kind of introduced. So I think back in 2009, right? And then I think this is exactly where the cumulative exposure model comes from. So a paper by Zhu. And then this paper is kind of not very recent, and back in 2021. So it says maximum precision estimation for a step stress model using two-stage methodologies. Right. And then one can, so just to give you a very simple idea, so now the current problem is done, but where exactly can you apply sequential? So one possibility is, let's say, stage life testing. So these days, I think stage life testing is kind of very widely analyzed. So stage life testing, a simple example could be, let's say, if you have a computer device, and then the computer device fails, but then the failure can occur due to multiple reasons. So let's say if the motherboard can fail, or let's say if some keyboard fails, or some monitor fails, something like that, right? So the cause of failure can come from different sources, right? So how do you incorporate those and then try to estimate the parameters and so on? So stage life means that you have different stages, right? And then the causes of failures can also change, right? And then this example is called as competing risks, because one cause is kind of competing with the other. So failure of motherboard is kind of competing with failure of keyboard or some other source and so on. So slight extension of, let's say, step stress and stage life, right? Yeah, and then I think this is the last idea. So let's say if you want to classify a new observation into two possible distributions. So again, one can adopt a sequential idea here. So if you have, let's say, two different inverse Gaussian populations, right? And let's say you get a new observation. So under what distribution should you put that new observation? Can be actually analyzed in sequential idea also, right? And then here we have something called as probability of coverage. So we ensure that the probability of coverage is at least some number, which is omega, and so on and so forth. Okay. Yeah, so I think the time is almost up also. Yeah, so probably I'll stop right here. And then if you have any questions, then I'm free to answer.
Thank you very much. Are there any questions at this stage?
Yeah.
We assume that failure time that the exponential.
Correct.
Is it possible to extend it to failure time to some gamma distribution?
You can do that, huh? So there may be work on Weibull distribution.
Weibull log normal.
Log normal. But again, it turns out that MLEs are not easy. So you require some profile likelihood technique.
That means when the more than one parameter, you have difficulties
in estimating using a standard MLE approach.
Okay.
Yeah. But work has been done on Weibull, and then even, as you mentioned, probably Lindley, some work has been done.
What about heavy tail distributions?
Heavy tail I've not seen in this context.
Okay.
When it comes to
it is in reliability context, heavy tails are not used or
not often.
Yeah. Thank you.
Sorry.
Yeah.
Why it is not really normal or Python?
Which one?
Like the failure.
Yeah, if we look at the graph, it should be either depreciating, like light bulb example, right? Exponential means the lifetime of bulb reduces drastically. So you want to model that in the failure distribution. So exponential, gamma, Weibull.
So in the case of light bulb, it's okay, fine. But generally, failure, for example, you make some product and then the product is depreciation.
Correct.
That's not really exponential all the time.
Correct. So you can tweak that slightly. Yeah, but normal may not be the correct choice because you want that symmetric. So failures may not be symmetric in nature and so on.
Just one right tail, for example.
That you can have. So some version of exponential where you don't have such drastic peak or something, you can use that.
We can use the Weibull distribution.
Weibull, correct. Yeah. Right. Correct. Okay.
And and I just wondered if I might ask a simple-minded
Sure.
question. When you have this stepped stress, and you put numbers on this on one occasion, like 1.5 and 2.5, but in practice, suppose I buy a light bulb.
Correct.
I want to know how long it's going to last.
Correct. Correct.
How the step stress adds stress.
Correct.
How do you gauge the extent to which, if you translate that back into the lifetime of the bulb?
Correct.
How?
So for that, to make use of that pilot sample we discussed. So you had to actually exhaust some 5 light bulbs or 10 light bulbs to find out the estimated lifetime of those, and then use that estimator in the future.
Where does the step?
So let's say you observe M. So in this 2-stage, you take some 5 light bulbs, estimate both the parameters, theta 1, theta 2, using that. And then using those estimators, you create that N, capital N. Sample, the final optimum sample size, correct. Right? And then, so after those many failures occur, then you have to change this test level.
Yes, I was intrigued that you mentioned at the beginning that the mean lifetime might be 30 years for a light bulb. It's not outside of my experience.
Correct. Just a random example.
Oh, thank you very much indeed.
I request Professor Happy to hand over the memento to Professor Sudhi. Thank you, professors.
Well, the final speaker in this session is Professor Iwsmga, who's going to talk on generalized inverses of matrices and linear complementarity problem. I was intrigued in having an earlier discussion with you that despite the time that you spent as in the Union of Ministries of Agriculture and Industry, you are determined to speak about mathematics, and I think this is an excellent idea, and I look forward to your talking. So, Professor Iwsmga has completed his MSc in statistics from Iwsmga University in 1976, worked as a lecturer, and then joined the Indian Statistical Services and retired in 2012. So thank you very much indeed. I look forward to the thoughts you've had since.
Okay. So I'm going to talk about these generalized inverses, with which almost all of you are familiar. If you a generalized inverse, for getting generalized inverse, there are various methods. There are different methods of getting generalized inverses.
Can you make it?
Yeah, it is full screen itself. No, that is PDF.
Oh, we are not able to see.
Can you increase the size?
Okay, no, it's a PDF file. So
The zoom it.
Possible to fit width on other page?
Yeah, it is true.
So there are various methods of getting generalized inverses.
And one of them is by considering the ordinary inverse. If you take a matrix A, a square matrix, we are going to deal with the square matrices. If you take matrix A, add another matrix C, which I call complement, that is rank complement. So that rank of A plus rank of C is the order of the matrix. And if you invert it, you will get a matrix G plus N. How we are going to get it? I will tell you. So this method of getting the G inverses of matrices, I call ICO, inverted complemented matrix method. This was introduced by the speaker, and then later on the statement was refined by Manjunatha and others. So that we will see what is ICO. Then we will see what is called a section of a matrix. When you are going to have a matrix, you write it as a sum of two matrices. So each part of the matrix that called a section. What is a section and how to get that section of a matrix? We'll see. Then we will see some applications of this process, this method. How we are going to use this section in some applications like quadratic minimization and linear models. Then, see in the application, what we are going to see, how to use this section in quadratic minimization with the constraint. Then, how to split a random variable into the sum of two random variables, uncorrelated random variables. And then we'll see how we will use this in Gauss-Markov model, and also in variance components model. Next. See, we call a matrix A1 as the section of a matrix A if A1 plus A minus A1 is equal to A, and these two matrices, they are disjoint. That is, the column wise range of A1 and range of A minus A1, they are disjoint. Similarly, the rows. Here I have taken A and B. A and B are disjoint if range of A and range of B, intersection range of B is 0. Similarly, for the rows. Now my G inverse is A plus C whole inverse is equal to G plus N. We are going to get G and N. How to get G? G is nothing but A plus C whole inverse A into again A plus C whole inverse. This is my G. So if you are having a number of matrices A1, A2, A3, all are disjoint matrices, and you add one complement to it, and take the inverse of it. If you take the inverse of it, you are going to get A1 bar, A2 bar, A3 bar. What are those A1 bar, A2 bar? A bar is A plus C whole inverse, A into A plus C whole inverse. So now, what are these A1 bar, A2 bar, A3 bar? A1 bar is a reflexive G inverse of A1. A2 bar is reflexive G inverse of A2, etc., etc. Now, if you take the cross product, A1, A2 bar will be 0. A1, A3 bar will be 0. So all the cross products will be 0. Now, this sort of approach, you will see in what is called minus partial order. In minus partial order, what we do, you take the matrix A and another matrix B, we say A is less than or equal to B in the minus partial order. When there is another matrix, you say D, we can write A plus D equal to B. In A and D are disjoint matrices. If you can add another disjoint matrix D to A, you will get B, then A is less than or equal to B according to partial order. So the partial order minus partial order, how we get? Keep on adding disjoint matrices. Take a matrix A, add one disjoint matrix to it, another disjoint matrix to it. So are going to get partial order, minus partial order. So our inverse complemented matrix method is how it is related to it. Just I am pointing out here like that. Now this in this, what you are going to, the C bar is the null matrix of A, because the cross products are 0. So A1 into C bar also 0, A2 C bar is 0, A3 C bar is 0. That is A into C bar is 0. Therefore, A bar, C bar is the null matrix of A. Similarly, C bar A is also 0. So it is row null as well as column null matrix. Now, if you take A1 bar, that is idempotent matrix. You know, A1 bar is a G inverse. It is 1-to inverse of A1. Therefore, A1 bar is idempotent matrix. Similarly, A bar is idempotent matrix. Now, since A plus C whole inverse into A plus C is equal to I, identity matrix, you get this equation. Sum of AI bar into AA plus NC is equal to I. Similarly, summation AA bar plus CN is equal to identity matrix. So as I mentioned already, this concept was introduced in these two papers. Next. Okay. Now I told you what is a section. A section is of A is B. So if A plus D is equal to B, then A and D are sections of B. If A and D are disjoint matrices. Now, how to get a section of B? The bigger matrix B, I want to get a section of B. That section, I know it has some column space and row space. So given a row space and column space of a section of a matrix B, how to get that matrix B? This F transpose, suppose range of A, E is such that range of E is contained in range of A. That is, range of E is contained in the column space of A, and range of F is contained in the row space of A. Then E F transpose A minus C minus F transpose is a section of E. So once you specify the row space and column space of that section, if you want to find out, identify that particular section, this is the way. You are given E and F And you can find the section of A in this using this formula. And this section may not be unique. Given E and F, if you are finding out this, why it is not unique? A minus is not unique, and for the entire expression, and again another G inverse that is not unique. Therefore, this expression, this is not unique, but it is a section. And in that section, what is going to be really the column space and row space, we don't know. That we have to explore. That depends on the A minus and the 1 minus. So, but if rank of F transpose A minus E is equal to rank of E is equal to rank of F. Suppose E and F are such that this condition is satisfied, then this expression is unique. That section is unique. You can find a unique section if the rank condition is satisfied. Okay. Now you see when I say the section E F transpose A minus, this E and F, they can be anything. If the range of E and range of F, that what matters. You can choose any matrix. You can choose any matrix E and F. If the range of E and that matrix, the range of that is the same, the result is going to be the same. It's range dependent. It's space dependent. It's not to be dependent on the exact matrix. And this result has been given by Manjunath in a different way. He has not directly given this result. He has given it in a different way. Nayan Manjunath, they have put it in a different fashion. But let us proceed with our definition of section. Now let us identify a section of positive semi-definite matrix. How to identify a section of a positive semi-definite matrix? If G is positive semi-definite and X is any other matrix with the same number of rows, then a section Gx, when I say Gx, for that section, the column space is the column space of X. Range of Gx is equal to range of no, here is the I am going to get a section of Gx from this expression. I think most of you are familiar with this expression. CRO has given this expression in the inverse partition matrix method in Gauss-Markov model. IPM, we call it IPM. And you find this expression. And this intersection, this Gx space of the column space of Gx is the intersection of column spaces of G and X. Whatever is in G and whatever is in X, the intersection of these two column spaces, this Gx contains that intersection. Now, similarly for rho also the same, because it is a symmetric, positive semi-definite symmetric matrix. This E and F, which I defined earlier, E and F, they are same. I am going to take a symmetric section. Therefore, that E and F is same, equal to X. So this we are going to use. This entity we are going to use for all our work in application. So though this entity is very useful in expressing very lucidly all those things in the analysis, somehow even CRO has not made use of it exclusively in this expression. this section. Now, GS is a unique section of G. I want to get a section of G with the column space given by X and row space given by X in this way intersection. Once you get that section, this is unique. That is a unique section. It doesn't depend on any G inverse, whatever you use for getting that section, it is independent of that. Whatever G inverse you can use. It's a unique section. GX is unique. So now therefore I can write this G plus C. C is a complement of G. Here you see note. The complement when I am taking C is need not be a symmetric matrix. Any complement. So G plus C is equal to Gx plus Gx bar plus C. When I say Gx bar, it is G minus Gx. So this Gx bar doesn't contain X component. Gx only contains X component. So G plus C is that. And if you take G plus C whole inverse, using that ICM, I'm writing. Using ICM, you get this. C is very complement of G.
Of G plus C is
invertibility of G plus C. That's what I said. G is the PSD matrix. C is a complement of G, mean rank complement. When you say complement, rank complement. So that G plus C is not similar. When you say complement, it is rank complement. So now let us see some applications of section. One is quadratic minimization. You are all familiar with this. Minimize X transpose dx subject to a constraint Ax is equal to B. Now let me take H is equal to A transpose for convenience. You will see why I am taking like that. Now X is equal to G bar X plus Gx plus etc. This expression is true. You forget about X, remove X and put here I. That's right. Because it is nothing but G plus C whole inverse into G plus C. G plus C whole inverse into G plus C is without X, remove X and put I. That is identity matrix. Therefore, now multiply by X on both sides. On the right hand side, you will get X is equal to this. Is right? Because the sum of these expressions is equal to I. Multiply on the right by X, you will get this equation. Now, what is X transpose Gx? Exponent Gx is this one, because I told you the cross products vanish. The cross product vanishes in ICM. Therefore, X transpose Gx is turns out to be this, and which is greater than or equal to B transpose this. Because if you insert the condition here, your Gx is GH is equal to H transpose G minus H minus H transpose. Sorry, I have to use here G plus H transpose whole minus H transpose. So taking that H transpose X is equal to B, applying it here, you will find that X transpose Gx is greater than or equal to this. So X transpose Gx is greater than or equal to this. So So the minimum value is given by B transpose AG minus A transpose minus B. So I'm not applying Lagrange multiplier or any other differential equation, math differentiation. I'm using this concept of section. I'm getting the minimum of this quadratic form. So what you are essentially doing is the range space of X I am dividing. I'm getting a subspace of G which is confined to X, the space of X. The remaining things I don't require. When I have to do this analysis with respect to X with the constraint here on X, to reduce that space G, range of G, to the space of range of X, and then concentrate on that reduced subspace. So we will get the result.
Which one gives you that this is many?
This one. Now this expression you can write it as X transpose Gx and a linear function of X. We reduce it, we expand it. So the expanded function yes comes through this, and X minus Q take it as user, some user. Yeah, X minus Q put user. And this material for your minimization. This is independent of X. Therefore,
we have to minimize
you can just minimize X, this part only. You can minimize that part only. So this expression you will get at many places, and our in the least square method in Gauss Markov for getting the minimum variance, you get such expressions. This is one important thing. I don't know. At least I'm happy about this splitting because it has various applications, very interesting applications. Now, this G plus C, this expression will agree? Because G plus C whole inverse is, you have seen G bar X bar plus N. So multiply, you will get this. Where G is Gx plus Gx bar, and G plus C is G plus C. Very good. G plus C is Gx plus Gx bar plus C, and G plus C whole inverse is your G bar X plus G bar X bar plus N. C bar I am writing as N. And you multiply, the cross products will be 0. You are left with this. So you are left with this. So on either side, now you multiply by epsilon on both the sides. You will get epsilon is equal to this part into epsilon plus this part into epsilon plus here n into epsilon will be 0 because variance of epsilon is G and n is normal to is a perpendicular vector to n is the null concept means pats the null space of G. Therefore, that product will vanish. Or you can write is equal to 0 with the probability 1. Because we don't want to leave out that even that very freak event of the epsilon taking some value in the null space of G. The probability 1 is. Now you are taking this random variable with the expectation 0 and variance G. Therefore, that is the case. Now, these two these two random variables are uncorrelated. These two variables, random variables, gx bar epsilon. This gx bar is the same as gx bar is same as gx g minus. Is that right? Because g minus is because g minus is your gx g bar x plus g bar x bar. When you multiply this g minus with the gx, only this part will remain, the other part, cross product will vanish. So I can write gx g bar x as gx g minus. Thereby, I'm avoiding that g bar x bar, etc. G minus. So gx g minus. So gx g minus epsilon and g x bar g minus epsilon are uncorrelated. And the gx is it is fixed. You don't require any g inverse. For x, given g, given x, gx is fixed. I don't require various g inverses. If I take a particular g inverse, you will get a particular section. No? Any g inverse you take, I am splitting g into gx and dx bar, and that is fixed. It is invariant. So gx is that g minus multiply by any g inverse of g. So these two entities are uncorrelated. How it is very interesting? Because for any epsilon, that condition is put, how to choose that epsilon belongs to n space of G? How to choose that for any epsilon that belongs to n space of G, then epsilon can be written as this, or how to choose that epsilon? Some epsilon. For any epsilon, it is true, or for some epsilon? I am taking any random variable. Any random variable epsilon with expectation 0 and variance G. Any epsilon. So,
just the epsilon should be in the range space of G. That's all.
Yeah, epsilon epsilon takes value in the range space of G.
Then only it will be.
Of course. Okay. When a random variable has variance G, epsilon takes values only in range space of G. Now, how it is important, this splitting? This, see, when I want to find out the minimum variance estimator, the minimum variance estimator, you want a particular estimator is minimum variance if the covariance between this estimator and any other estimator zero, keeping zero estimate, zero expectation, the covariance is zero. This Basu's theorem. So for getting the minimum variance estimator, this is very useful. When you are splitting a random variable into two parts, uncorrelated, then that will help us to get the minimum variance estimators. So now let us come to the Gauss-Markov model. Y is equal to x beta plus epsilon, variance of epsilon is equal to G. Now the Y belongs to here, Y belongs to not only G, range of G, it belongs to range of X also. It is the sum of the two spaces, not the direct sum, because they are not complementary spaces. So it is the sum of range of G plus and range of X. Now the variance, I am going to take another entity here now. I am going to define V as G plus X transpose G bar. So what is this X transpose G bar? You know, already in G, this X component is there. This X component is there already in G. Now I want to choose a complement of G for the purpose of applying ICM. I want to apply ICM. I require a complement, a rank complement. Now I have to choose a C. For choosing C, what I do before choosing any other C, I am adding this rank complemented Gx bar. No, rank complemented X transpose G bar. X transpose G bar means whatever is there in X transpose, not in G. X transpose G means whatever is there in X transpose, which is in G also. So my X transpose G bar is the stands space of X, which is not in G. So whatever is already in G is here, Gx. Whatever is not in X is here. So if you take Gx and this two, this will span both G and X. It will span the space of G plus X transpose. So it will span X space will be spanned by Gx and this. And whatever is not there in X, that is given by Gx bar. The total, if you take, this will entire thing will span Gx transpose. Then to this you add C. So with such a C, now I can, as I did for splitting random variable, I am splitting Y into these components. First component is all containing X in G. All components, whatever common to X and the range of G, that is given here. And here, whatever is not in X, whatever is not in G, Gx bar. Then X transpose G bar, and then finally the complement. Now the first, this I write as Y1, Y2, Y3, Y4. So this is my splitting of Y. My claim is all the history about this GGM is contained in this book. We need not go anywhere else. Think about projection operator. Think about any other space. Everything is here. This sort of splitting is given by Nordstrom. I think it was in 1983 or so. And this is mentioned in Sengupta and Srinivasa Rao in their book on linear models. So they have given this, and now you see, as I already mentioned in the splitting of random variables, these Y's are all they don't depend on C. Whenever I use a complement, I can use any complement. The complement I have not fixed the rank complement matrix C. So I can take any complement. Therefore, I can take any G inverse. So it does not depend on that. Now Y4 is 0 because back. This is y4. This y4 is 0 with the probability 1. Okay, next. Y4 is 0. Expectation of y2 is also 0. Expectation of y2 is 0. Y2 is what are those in G which is not in X? In our model, x beta plus epsilon, when you are going to take epsilon, it is expected value is concerned with x beta. Now this part y2 does not contain x. So expectation of y2 is 0. This 1 to the yi, all these 4 entities are uncorrelated because I have already told you in splitting epsilon, the two are uncorrelated. So therefore, these 4 entities are uncorrelated. This entity y3, this is our entity y3, x transpose g bar. Anything? No. So this x transpose g bar, this is our this part. This is not in G, it is outside G. And C.R. Rao's paper on representation of blue, he very much concentrates on this. He concentrates on this. Now for getting blue, what you require is y1 and y2 only. Blue is a function of linear function of y1 plus y2. Blue is a function of y1 plus y2. And this x transpose GP requires some attention because one paper is given by C.R. Rao. That x transpose this part y3, that is independent of G. It is only involves x only. And it is independent of epsilon. It is degenerate random variable. Y3 is a degenerate random variable. There is no epsilon part. There is no epsilon part. It's a degenerate random variable. But then this y3, y3, where are you? X transpose G bar, G inverse, G minus Y. This is your Y3. This Y3 is free from epsilon. And if it is free from epsilon, that is only simply a single vector. That x beta, when you take the expected value of this, you are getting x transpose G minus x beta. This entity, since already whatever, you need not even take a expectation because this y is independent of epsilon. Epsilon is not there. So this entity is simply this. So whatever the observation you may take, y, if the model is correct, then this entity is simply a constant vector or single vector. But then this matrix, if you take, it is not a single column matrix. Number of columns are there. But it is the result, when you multiply by y, you are going to get a particular vector. So this is what C.R. concentrates on this paper, representation of blues. And many papers, we don't bother about that property. It's a single vector. Okay, then so as I have mentioned, the the blue of lambda transpose H beta is simply this. And then I have added this my4 because my4 is 0 with the probability 1, but then we put it there. Okay, and then so the usual question will be how to minimize with the restriction. With the restriction, say how to minimize with the restriction x1 beta is equal to b, and that also we can get by using these. So how long I have been saying I have been using the rotation gx, gx1, etc., etc. So I am applying this section and getting all these expressions for these estimates. So you will get this expression, the conditional minimization. X1 beta is equal to b. Condition. Next. 1 minute. So let us come to this variance component model. Unless you are all tired, you can disperse for lunch. I will take only 2 minutes if you are interested. So variance components. The variance component model you know. And the variance is U transpose if you take the variance of this. So let us call U transpose P and then VB transpose Q. Then what I am doing is I am taking A as P minus Px. Px is what? Whatever we know the section of P. So this A is doesn't contain X. I am removing this part. Removing this part X. Similarly, B is equal to Q minus Qx. Now I take this A plus B I can write as A minus AB plus AB plus BA plus B minus BA. And then these two, AB and BA, they have the same space. How much of B is in A or how much of A is in B, that intersection, the same space wise same. The matrices are different, space wise same. Therefore, if you add these two, you call D this same space. D is equal to AB plus BA you take. And then, so AB plus B minus is this one you will get. Now, range of AB or range of BA is the same as I told you, it's range of D. And with this, you will get now the trace of AB bar A square, you will get from this estimator. So this estimator, I am using these 6 sections. This estimator gives you trace of AB bar A square. Similarly, this expression gives you trace of BA bar B square. Therefore, you get A square and B square from here. The estimators of A square and B square you get. And the third expression gives you trace AB A square plus trace BA B square. Already you have got A square and B square. Substitute here, you will get already we have got A square and B square. So you will find this is the estimator of this linear function of A square and B square. So this is one way of finding the variance components by using this sections. And I have used this only for A square and B square, two variances, A square and B square. This can be extended, this technique can be extended to more than 2, up to n, by using some algorithm program, how to get those A1 square, A2 square, A3 square, etc., etc. So this is an application of a section. It has many other applications in my view, because so much of literature is there on outer inverse, G inverse, this and that. But this method, ICM unifies everything, and this section helps you to visualize things directly without involving so much of projector, this and that. So this is what I.
Thank you very much. I think we're dangerously close to lunchtime. But I perhaps you could entertain one question, if there are any. I found your talk very interesting in the sense that results kept coming up that I've looked at in a different way. So I think it would take me a while to understand, I think, exactly what the links are. But I think the very nice thing about your talk was that this mysterious XX transpose that keeps getting added to G is it's a little clearer where it's coming from. I mean, I can see that it's basically to force the new covariance matrix to fit into the column space, so that X is now the column space of X is now the column space of V. So I think it's very interesting. So thank you very much indeed. Thank you.
I request Professor Haslett to hand over the memento to Professor Iclaa.
Thank you.
Thank you, Professor, for sharing the session too. It was our pleasure. And we are breaking for lunch now, and we'll be back in an hour. Maybe at 2:20, we'll get back here to start the next session in the afternoon. Thank you.
Participants, there is a small announcement. Those who are joining us for the cultural event in the evening are requested to gather downstairs, maybe 10 minutes before 4 o'clock. Bus will start sharp at 4 p.m. today, before time. So afternoon session will start exactly at 2:30 p.m. today. And tomorrow we will start the morning session exactly at 9 o'clock. Tomorrow session. Thank you.
Which technique you use to section for decision to study about modern citizen of validation technique for
Then from here,
yes,
You are not running. You have to push space. Then Emerson Of the decomposed thoughts. Like, for example,
Before instance.
but make it 5 minutes.
Yeah, I don't have it.
Like that.
Right, so,
I don't remember Kennedy that much.
that's this one. But the thing I find is this, but why? Really is no problem. You understand what's going on.
Yeah, because we have a nice differentiation here that we get.
But when this isn't, seems to be really what, so there isn't, what Rao's trick is, going back to the example in this one. So, that's, it's allowed to provide some of this. It's tricky. This is new, as you said before, so this is the condition which right using this one and then continuing to move it. This is not intending on its place so I think there's a side street. I agree with you, there's a clever side street.
Yeah.
Yeah, I can't put my finger on it.
But I think
it's section is
Recording and stop.
not.
And this will fit somewhere, of course, or maybe when you take something of solver to be, then you can blow up in some way.
Yes, but I think using this avoids just sort of a.
But I'm not sure because what we did, everything was about how to define gender.
Yes.
And then in some generalized inverse or some choice of it, you can do it like this. But you have other choices also.
Yeah. This choice is one of many.
Yeah.
Well, I think it just you just use.
Yeah, because you get have choices of generalized inverse where you
Yes, every part of all the stuff about section is really just hiding the
It will be late coming. Only one bus is there. One was late.
it's not always important. But
So it's going to go.
bias, not
Only
space.
one come, that is.
ಹಾಗಿದ್ರೆ ಅರ್ಜೆಂಟ್ ಮಾಡ್ಬೇಕಂತಿಲ್ಲ ಅರ್ಜೆಂಟ್ ಮಾಡ್ಬೇಕಂತಿಲ್ಲ ಬೈಯೋ ಯಾರಿಲ್ಲ ಸ್ಟಾರ್ಟ್ ಮಾಡಿದ್ರೆ ಆಯ್ತು ಟೈಮಿಗೆ ಇವರೆಲ್ಲ ಕರ್ಕೊಂಡು ಬಂದ್ರೆ
ಯಾರು ಹೋಗ್ಲಿಕ್ಕೆ ಆಗುದಿಲ್ಲ ಬಸ್ ಇರಲ್ಲ.
Because you can take anything of solver. Then solver can be some. You have to pause it. Sense. You have to assume something on why, but you should have told, because otherwise the data will not you're not satisfied in this.
No, exactly. Because the metric you're measuring it doesn't contain it. So what's it? It doesn't contain some part of it. It doesn't contain some part of it. What's it going to do with the rubbish?
When the old buses. They're spoiling the whole night.
We're spoiling it. No, oh, sorry. Yes, okay.
It's just that getting back to believe.
Yeah, come. Shall we go? Okay. I really can say. Sir, you want to keep your bags here?
No, I just want to go to the front.
Yeah.
Sorry.
Sorry.
Sir, I'll do that, sir. Yeah.
No problem.
Thank you.
अवनीत 1 मिनट आएगी.
This this was Is it correct?
Yeah.
Control instruction.
I'll ask. How are you?
Welcome back, everyone. So let us start with the afternoon session of day 2. In this session, we have the following speakers: Professor Shivaramakrishnan Shivasubramaniam and Professor Ajit Iqbal Singh. I now request Professor Kuncham Sham Prasad from Manipal Institute of Technology, Mahe, to chair this session.
Very good afternoon, everyone. Today's first session in the afternoon by Professor Sivaram Krishnan Subramanian from Indian Institute of Technology, Bombay. Title of the talk is Maximum 4-Point Condition Matrix of a Tree. And Professor Sivaram Krishnan's research interests matrix theory, graphs, combinatorics, combinatorial optimization, discrete mathematics. He has published more than 25 research articles in reputed national and international journals. I welcome you, sir, to start the session.
Yeah, okay, so I'd firstly like to thank the organizers, in particular Professor Manjunath Prasad, for this invitation. I've been coming to Manipal so many times, maybe 7 or 8 times I've come here. So I've lost track actually of the exact number, but let me say, it's N for a large N. Huh? Because first, second, and third trips, maybe you'd remember. Beyond that, nobody counts. So I've also lost track of the count. And it is like a second home to me. I know many people here, in particular, many of the organizers I know, like Vinay Madhusudan, Uma Shankar, David. I know all of these people now. So, and I've been coming here for over a decade now. So I'm very happy to be here once more. And so for this, I would like to express my gratitude to the organizers. And I'm going to talk about this maximum 4-point condition matrix that is associated to a tree. So this is joint work. Okay, so this pointer doesn't work, but that's okay. It is joint work with Ali Azimi. So Rakesh Jana is a postdoctoral fellow at IIT, and he's doing his postdoc with me. Mukesh was my earlier student. So this Ali Azimi, he had once come to India. He was from Iran. Now he is working in Malaysia. He had come to India once to visit Bapat. And then Bapat told me that after he had planned, he was not sure when he joined. That is, when he came to India, he was not sure how long he should plan everything. So then he told Bapat he'd come for a week or something, and Bapat said fine. But then he had already planned for 2 weeks. So in 1 week, he was there at Delhi. And then Bapat asked me, can you host him for a week? So I said, yeah, come over. And then, so at that point in time, we didn't do anything. But then subsequently, we started working. So after that, I've written several 2 or 3 papers with Ali Azim. So this is the very, how I started working with this person, Ali Azim. So the names, if you look at it, 3 are clearly, Indian names. Clearly, this you may not know, but yeah, he's from Iran. Yeah. Okay. So let me start with distances and graphs. So in general, if you are given a connected graph, the distance matrix, that is, so let's say the graph has n vertices. So you can get an n cross n distance matrix. So the ijth entry will be so in row I, column j, the entry will be the distance between vertex I and vertex j in the graph G. Because the graph is connected, this dij will not be infinite. That is, it will be a finite number. Yeah. And this has been studied well. No? If you look at this distance matrix, there are good results, like starting from Graham Pollock, Graham Hoffman, Hosoya. There are quite a few interesting results where, this algebraic properties of this distance matrix is studied. Yeah, it is a very, very well studied area, and in fact, spectra also is done. Though I will not cover much into. I will not go into spectra for this talk. Yeah, and sometimes you have to invert the problem. So what do I mean by invert the problem? So there are these. This is done by biologists
more done by biologists. So there they have some species, let's say viruses, yeah, and then they measure some parameters of the virus, and then they say this virus is this close to this other virus. So then they have this general belief that viruses now have evolved over time. So every virus is a mutation of some other virus, mutation of something else. So there is this tree structure that they believe exists. So we think there is a tree structure. Even in evolution, they think we are very close to some ape. So we are like one of the bottom. We have not given rise to more species, but we are like a leaf in that sense. So there is an evolutionary tree. So why is the evolutionary process a tree? That for that biologists have some reason. Why is it not? Why are there no cycles? For that biologists have some reason. So since I don't do much of biology, I will not answer that. But it is believed that the evolutionary process is a tree. Yeah, and because we can only measure how close two species are, we are actually given the distance between two species. And then we want to see if there is a tree which gives rise to this distance matrix. Is this clear? So people in biology try to invert this problem. That is, given a graph, getting the distance matrix is easy. There are algorithms, Floyd-Warshall algorithm. There are quite a few algorithms. Now we are given a distance matrix, and typically it is weighted, because if you have unweighted, if you look at the adjacency matrix, all edges which is distance 1, they will already be there in the distance matrix. So if your graph is unweighted, the problem is not interesting. You can recover the adjacency matrix from the distance matrix. But if it is weighted, you don't know. So you have a weighted distance matrix, and you want to know, does it arise from trees? So is there anything special about distances that arise from trees? So this was what was of interest to biologists. And this person called Buneman, he showed that indeed tree distances can be recognized in the following sense. So suppose you are given a distance matrix, that is, there is some finite metric space, and you are given the distance matrix of this finite metric. That is what I call as this D. Suppose you are given this. So this Buneman's condition, it says you take any set of 4 points. Yeah, so I'm calling it I, J, K, and L. So if you take 4 points now, I, J, K, and L, clearly there are 3 perfect matching. So one is this vertical, I, J, K, L. Then or you can take this horizontal, maybe I, L, K, J, or you can take the cross, I, K, J. Yeah. So you look at this. So I'm calling it a multi-set because some of the terms maybe, if you take the addition of these, some 2 terms may be the same. Yeah. So that's why I'm calling it a multi-set. It may be a set, may be a multi-set. So I just call it a multi-set. But this 4-point condition will tell you indeed that it is a multi-set. Yeah. So this 4-point condition, it says that among these 3 terms, the maximum value is equal to the second maximum value for all set of 4 points. Okay. So let me just repeat what it is. So you take 4 points. You are given a distance matrix. You want to know whether this distance matrix arises from a tree. So you check for all set of 4 points, I, J, K, and L. You look at this set S, I, J, K, L. So you think of it as a multi-set. Yeah. You check whether the maximum value in this multi-set is equal to the second maximum value in this multi-set. If this is true for all set of 4 points, I, J, K, and L, then these distances arise from a tree. This is the condition of Buneman. Yeah. So what Buneman says, yeah, so let me see. So graph is a tree if it is connected has no triangle. So tree satisfies the 4-point condition. So this 4-point condition, I'm going to abbreviate as 4PC, yeah, for this talk. Yeah, so this 4-point condition. So Buneman proves 2 results, one in each direction. So if it is a tree, then the distances of a tree satisfy the 4-point condition. That is the easier part, which is theorem 1. And the second theorem, which is the only if part, that is, if some distance matrix satisfies the 4-point condition, then so there is a weighted tree which contains the elements of S among its vertices. Because see, if you have a distance matrix and it satisfies some condition, you take any principal submatrix, that is also likely to satisfy this condition. So you won't know whether your matrix is actually arising from some larger tree. So that is the extra thing that you may not know, because any induced principal submatrix of the distance matrix will also satisfy. For it to be a distance matrix, you want diagonal elements to be 0, you want symmetry about the diagonal, and you want triangle inequality to be satisfied. So if you take any principal submatrix, they will also satisfy, that will also satisfy these. So the best you can do is this, that is Guneman says tree, if you take a weighted tree, so when I say weighted tree, the edges have weights. Then distances that arise from a weighted tree also satisfy 4-point condition. That is the first part. The second part says if this 4-point condition is satisfied, then there is such a tree with some weights that you can assign on the edges of the tree, and I'll tell you what subset of. So you look at that distance matrix on that tree. So suppose your given distance matrix was n cross n. I will give you a tree with more than n vertices, and I will give you a subset S of size n. So you look at that distance matrix on that tree, which is more than n. So it is maybe some n plus k cross n plus k, and you restrict it to the principal submatrix on some set S. Yeah. So that's what this second portion of Guneman's theorem tells you. So this is the, it tells you that these tree distances are slightly special, that is they are a little more general. So in fact you can check that this is stronger than triangle inequality. If among these 4 points there are only 3 distinct elements, you can check that you get the triangle inequality. So this 4-point condition is a little stronger than triangle inequality, and then you can get a little more. Okay, so in this work, so I will start with a tree. Yeah. So this at that point of time, so I tell you at that point meaning at around 2018-19. So I was studying lots of properties of trees which are independent of the tree. In the sense, the result will only be dependent on the number of vertices in the tree. It will not depend on which tree. So all trees on n vertices will give rise to the same result. That is what that. Such a property I call as tree independent. So I was studying a lot of tree independent properties. I'll give you one in a while. And in the course of that, we had defined this matrix. So let me define the matrix, and then I'll tell you what I mean by tree independent results on trees. So you take a vertex on n vertices, that's our starting point. So of course its distances will satisfy the 4-point condition. This is due to Guneman's theorem. So we define these n choose 2 cross n choose 2 matrices. So I call it min 4-point condition matrix of the tree T, the average and the max. So what is the definition? So when I say you take n choose 2 cross n choose 2 matrices, of course the rows and the columns are going to be indexed by unordered pairs of vertices. So for example, ij is a row, kl is a column. So what is the entry in row indexed by ij, column indexed by kl? So you look at this set Sij kl, which is this multi-set. Yeah, it contains these 3 elements, and in the min 4PC matrix, you put the minimum entry of this multi-set. For the max, you put the maximum entry. For the average, you put the average entry. So as of now, this average may be half integral. That is, it may be that the max, one of these is odd and the other is even. It is possible. In which case, if you take the maximum, you will get a half integral matrix. It is possible, but we will see it is not possible. From the definition per se, it is not clear that all of them are integer matrices, especially the third one. The first 2 you can, because I'm taking the unweighted version, yeah, for now. So the first 2 of these were studied, and in this talk I want to talk about the third one. So I'll tell you which 2 were already studied, and let me illustrate this matrix. So I'll illustrate all 3, but I will start with the minimum 4-point condition matrix. So here is a tree. Since I said I'm taking unweighted tree, so the weights are 1 on every edge. So let me illustrate one entry. So is it clear that the tree is symmetric? That is, the distance matrix is symmetric. So 1, 3, 4, 5 entry and 4, 5, 1, 3 entry. They will be the same. Yeah, that is the first point I want to make. And so if you want to compute the entry in the row indexed by 1, 3, so I'm writing, instead of writing flower bracket 1, 3, I'm just writing 1, 3. Yeah, that's just for. And here, instead of writing 4, 5 in flower brackets, I'm just writing 4, 5. So what is the entry here? Row 1, 3, column 4, 5. So you look at these 1, 3, 4, 5. So what are the 3 perfect matchings? So 1 to 3, 4 to 5. So this distance is 2. This distance is 1. So they have put in a different color, I think. Yeah. So this distance is 2, this is 1. Likewise, you could have 1, 5, 4, 3. So their distance is 3 and 2, and 1, 4, 3, 5. Here also it is 2 and 3. Yeah. So the colors will give you the perfect matching, and the appropriate distance is also written with the same color, just to check. So if you look at this multi-set S1, 3, 4, 5, so it has the elements 3, 5, and 5. So 3 is because 1 plus 2. Yeah, 1 plus 2 is 3. One of these 2 plus 3 is, one of them is 5. Another 2 plus 3 is also 5. So when I say take the minimum, so what will the entry be? You take the minimum of this, which is 3. Yeah. So definitely because of symmetry, here also 4, 5, 1, 3, that will be the same. But I want to point out that there is a lot of redundancy. So just like 1, 3, 4, 5, the entry is 3. If you look at 1, 4, 3, 5, that entry will also be 3 because you're taking the same set of 4 points. Yeah. So there is some redundancy here. Likewise, the entry 1, 5, 3, 4. So symmetry is going to be reflected by a slightly different color. But these, so this is equal to this, that's clear. This equal to this is clear. These follows from symmetry. But these are also the same because of some redundancy. Because whether you take 1, 3, and 4, 5, or you take 1, 4, and 3, 5, you're taking the same set of 4 points. So this set 1, 3, 4, 5 is the same. And you're taking the minimum among what set? That set is the same. So there is some redundancy in this matrix. So this is the thing that I wanted to say. So let me illustrate one more entry in this. Okay. So here, so it may be the case that your Sijkl, when you think of it as a multiset, has only one distinct element. So here I'm taking S. So 1, 2, 3, 5. So you look at 1, 2, and 3, 5. You look at it again. So all the entries. So there are 3 perfect matchings: 1, 2, 3, 5, 1, 3, 2, 5, and 1, 5, 2, 3. All of them will give you 4. So if you look at some of these two distances, it will be 4. Some of these two is 4. Some of these two is also 4. So it is possible. So that's why this is 4 here. Yeah. Of course, symmetry is also there, but and there is this redundancy. Yeah. So let me go to the max entry. So max, is it clear that here the 4, 4, 4 will remain 4, 4, 4, whether I go to from min or max, because the set is going to be the same. So in the max, the color should have changed. So 4, 4, 4 will remain the same. But these 3s, the 3s will change to 5s. Is it okay? So let me just go back. This is the min 4PC matrix. This is the max 4PC matrix. The next slide. Just that some entries will be the same, some will be different. Yeah. And here is the average. So this is also called the 2 Steiner distance matrix. So what is the definition? So can people see this? Okay, it's clear for me, but at the back. If you can't see, it's okay. This is symmetry. You should be able to see one of them. Somehow in this color is not looking good in this screen for now. This background also looks very white to me. It's actually somewhat yellow. So that's okay. Just that our lighting, ambient lighting. So how do you? So I said no. It is possible that maybe this entry is odd. The other entry in one matrix it may be odd, and the other it may be even. And hence when you take average, you may get half integral values. But so this example doesn't prove anything, but I'll tell you what it is. If you look at the entry in 1, 3, 2, 5, let's say 1, 3, 2, 5, you look at the number of edges in the smallest subtree, which contains these 4 points. That's what you have to do. You look at the number of, so why is this 1, 2, 1, 5, 3, 1, 2, and 1, 5? So what is the size of the smallest subtree that contains these 4 points? Here, point 1 is appearing twice. But if you take this edge, and this edge, 1, 2, 2, 4, and 4, 5, you would definitely get a path. I mean, you would connect up all the 4 vertices. So this shows that this interpretation, that is, it is the number of edges in a smallest subtree containing these points I, j, k, and l. Because with the number of edges, it cannot be half integral. Yeah, that's the reason why if one of them is odd, the other will also be odd. Yeah. All right. So these are the 3 matrices. No, this is I've covered all 3 matrices. So this is the min 4PC matrix for this tree. This is the max. 4PC matrix for the same tree, and this is the average 4PC matrix or the 2 Steiner distance. So 2 Steiner meaning, see, this notion of distances was generalized, and there is the name to Steiner distances was actually given in this book by Courant and Robbins. Courant, yeah, what is mathematics? So what is mathematics is a good book. Have you read it? It's a very good book. I strongly recommend it. So it is there from that book. What is mathematics by Courant and Robbins. So it is there in German. It was initially written in German, then it's translated meaning long ago. So there they call these as Steiner distances because it was found that Steiner had done it. The origins go back to Steiner. So there, if you have some set of points P and Q in your graph, you can define it for any subset of points. Usually distance is defined between a pair of vertices, distance between I and J. Here now you can define distance for any subset P and another subset Q. So how do you define it? You take P union Q, that is again a subset. You look at the number of edges in the smallest connected subgraph of G such that all points in P union Q are connected. So then you can check that if the subsets are all of size 2 here, subsets are of size 2 here, if the subsets were to be of size 1 and size 1, what would you get? You would get an n cross n matrix. And what is the entry? Dij. It will actually be the normal classical distance. So when this is called the 2 Steiner distance matrix because the rows and columns are indexed by 2 element subsets of the vertex set. If instead you were to index the rows and the columns by 1 element subsets of the vertex set, you would get an n cross n matrix, which is the classical distance matrix. So in some sense, this is the higher analog of the distance matrix. When so you can define the k Steiner distance matrix of any graph. When k equal to 1, you will get the normal distance matrix. When k equal to 2, you get the Steiner distance is very well defined. For a tree, it so happens that the Steiner distance is the average of the min 4PC matrix and the max 4PC matrix. Their average happens to be this. So it's a very interesting fact that this happens. So this min 4PC matrix is the first matrix that was studied among this in chronological order. So this was done by Bapat and myself in 2020. So this appeared in 2020. So we had done it by 18 or 19. I don't remember now. So if you take a tree on n vertices, you start with a tree on n vertices. So what is the rank of the min 4PC matrix? So the rank is actually n. Even though it is an n choose 2 cross n choose 2 matrix, it is not a full rank matrix. It has only rank n. So what can you can ask, give me a basis for the row space. So you take the 2 subsets, that is the subsets of size 2, which correspond to edges of the tree. So there are n minus 1 of them, and you add an f, where f is not an edge. You take any such, so just take all the edges of the tree, that there are n minus 1 of them. You take any f which is not an edge of the tree. So let's say f is uv, it's a 2 element subset. So let's say it's uv. So and the distance in the tree between the 2 vertices u and v will be some number which is greater than 1. If it is 1, it will be an edge, and I've said f is not an edge. So this, suppose it's this distance, whatever be its distance, it is always a basis. I'll choose the case when, the simple case when this distance between u and v is the endpoints of f, which is the extra element apart from the edge set of t. So if the distance is 2, that is also a basis. And if you look at this min 4PC matrix restricted to the elements from a basis, so its determinant we found out, it is precisely this. And those of you who know this Graham-Pollock theorem, which gives you a determinant for the distance matrix of a tree, you get exactly the same. Yeah? So this is what I've written here. Properties of this min 4PC mirror properties of the distance matrix of a tree. So this is the same, this. And if you look at further the invariant factors, that is those which appear in the Smith normal form of this min 4PC with respect to a basis. So you get 1, 1, 2 n minus 3 times, and 2 into n minus 1 once. This tells you, up to sign what is the determinant. So when you take Smith normal form, it gives you a factorization of the determinant. But the sign will not be there because that will go away when you take GCD. GCD of 2 numbers is always somehow considered to be positive. Yeah. So because of that convention, the sign will go away, but otherwise the product of these will be the determinant in absolute value. That you can check. So definitely, if you look at this, no, this is not dependent on the tree T. So this is what I was saying, that there are some properties which are independent of the tree T, but only depend on the number n of vertices. So at that point, we were studying this, both myself and Bapat. So we came up with yet another matrix, which is tree, where the results are tree independent. So the definition of the matrix involves the tree T, but the result does not involve anything about the tree T except its number of vertices. Yeah. So that is what we did. This is the first thing I wanted to say. The second thing is, so when we studied the two standard distance matrix, so this was done by Ali Azimi and myself. So we showed that, here this rank is not tree independent. So if you look at the previous result, so it says rank is n, which is the number of vertices. So it is tree independent in the sense it only depends on the number of vertices. The second matrix, which is the two standard distance matrix, which is also the average 4-point condition matrix. So there the rank is not tree independent. It depends upon. So this I would like to say it is n minus 1 plus n minus p. So p is the number of leaves or pendant vertices. So it is actually equal to number of edges, which is n minus 1 plus n minus p. Number of edges plus number of non-pendant vertices. That is the rank of this two standard distance matrix. And we gave a class of bases. There is an inductive class of bases that you can. So if you want to get a basis for the row space, see the n minus 1 is the number of edges. So that anyway, if you want a two element subset, n minus 1 of them, you can choose the two endpoints of the take any edge, think of it as a two element subset. That will give you. Now for this n minus p, so as I said, this is better thought of as n minus 1 plus n minus p. So for n minus p, we needed some set whose cardinality is n minus p, because then you can use the elements of that set to index an element of your basis. So this is reasonably straightforward. If T is a tree on n vertices with p leaves, then the number of blocks, so blocks is maximally two connected subgraphs of the line graph of T is n minus p. This is, you can prove this by induction on n. Okay. So using that, we found out we gave a basis for the row space of the two standard distance matrix of T. And just like in the normal distance matrix, the inverse was found by Graham and Lovash, where they said it is the inverse of the distance matrix is actually scaled Laplacian, it usually minus half, I think, minus half Laplacian plus some rank 1. So VV, just like you have VV transpose here, there they had an explicit vector tau transpose. So, and there would be some other scalar here, 1 by 2 into n minus 1. That's okay. So your distance matrix was negative of some Laplacian, scaled Laplacian, plus a rank 1 matrix. So it's a rank 1 perturbation of the scaled Laplacian. That is what was proved by Graham and Lovash. So we prove something very similar for so that is the distance, for the one standard distance matrix, which is the distance matrix. For the two standard distance matrix also, you get a similar thing. You look at, because I want it to be invertible, you take a basis, you restrict your D to be having only the two standard distance matrix, restricted to elements from the rows and the columns of the basis. And then the inverse is here again. So when I say Laplacian-like matrix, it has row sums 1, column sum 1, the symmetric. Right? Explicit entries are known. Yeah? And there is a vector V. So VV transpose will make it rank 1 matrix, and it's a scaled version. That's okay. So this we had also done. This is inspired by the result of Graham and Lovash. So this was known. So let me just look at what is known. So we actually looked, when Bapat and I had done this thing about the minimum 4PC. So that time I said we were studying tree independent results. We looked at the max also. We knew it was not tree independent. But what was it? We didn't know. So we didn't know what would it be? We didn't know. So if you look at known results, so I have a column for every matrix. So min, max, and average. So the rank here is n. Rank here is 2n minus. So n minus 1 plus n minus p. So do you have a basis? Of course, for both of this here. Here Smith-Normal form was known, so that alpha is here. So 0, you can actually make it to be the Smith-Normal form of the entire matrix. So 0 occurs with this nullity, which is n choose 2 minus n. 1. So this is actually the earlier result. I'm just stating it here. So the inertia is also, it has one positive eigenvalue, n minus one eigenvalue. So gamma is the inertia of the min 4PC that I did not mention because I didn't want to put yet another slide for that. So one positive eigenvalue, n minus one negative eigenvalues, and of course 0 will be the rank minus the dimension, the n choose 2 minus the rank will be that many zeros are there. Here also average one positive eigenvalue remaining n2n minus p minus 2 negative and n choose 2 minus that many zeros. So inverse, it's actually a later result, but for now we know an explicit inverse here. We know an explicit inverse here. But for the max 4-point condition, we do not know anything. And so what I want to state is this. So this is in joint, as I said, joint with 4 of us. So the rank of this max 4-point condition matrix is twice n minus p. Yeah? So n minus p is the number of non-pendant vertices, twice n minus p. And we have an algorithm whose output will give you a basis for the row space. Yeah, and the algorithm is like depth first search. I'll tell you. I'll give you an illustration here. And if you look at the max 4PC matrix restricted to elements from the basis, so you can get the determinant value. So up to sign, this sign is also this minus 1 to n minus p, 2 to the 2 into n minus 1, p minus 1. So this is some determinant value we have found out. And likewise, if you look at the inertia, so I said rank is 2 into n minus p. So n minus p are positive eigenvalues, n minus p are negative. It's not symmetric, unfortunately. For many matrices, sometimes the eigenvalues are symmetric, but not in this case. Eigenvalues are not symmetric, but nonetheless there are, number of positive eigenvalues is n minus p, number of negative eigenvalues is n minus p, and number of zeros is n choose 2 minus 2 into n minus p. And if you look at the Smith normal form, the invariant factors, so I said here that the up to sign 2 to the 2 into n minus. So here also you can check that first two non-zero invariant factors are 1 1 and then it's 2 2 2 2 2 so on. Yeah. So we found out the Smith normal form also. We have the inertia of the max 4-point condition matrix over 3 as well. So this is yet another. So this we have submitted. I don't know, maybe it will get accepted. I don't know. You have to see. So let me state these things. So rank here now is 2 into n minus p. Here we have a basis, and I will illustrate this basis algorithm shortly. And Smith normal form, yeah. So here we don't have here. We have 2 into n minus 1 here for the min 4PC matrix. So the colors, somehow you try to match the color. Huh? Are the colors visible, especially at the back? Yeah. Otherwise, yeah. So here this is not there, but only has 1s and 2s. Yeah. And so we have the signature here as well. How many positive eigenvalues? So EVS is just eigenvalues, just short. If I write it too big, it goes beyond what I can fit into one screen. So inverse explicitly, here we don't know. Here the Smith normal form we don't know. So some question marks are there. So if anybody wants to work on it, I'd be happy to tell you whatever I know. So if you can solve it, it'll be good. Okay. So this is just a repeat. This is just repeating that the number of blocks in the line graph of T is n minus p. Yeah. You take any tree on n leaves on n vertices with p leaves. The number of blocks in the line graph of T is n minus p. So if you want to give a basis, so as I said, the rank is 2 into n minus p. So we will try to give. So we use this number of blocks as our indexing set, and the algorithm will output 2 elements per block of the line graph of T. Yeah. So I'll illustrate that on a. So it is somewhat inspired by this depth first search. So firstly, this star trees. So because rank is 2 into n minus p. So if you take a star tree on n vertices, it has n minus 1 leaves. So n minus p will be 1 because p is n minus 1. So n minus 1 will be 1, and twice that will just be rank 2. So there, that's easy. And the thing is, in a star tree, there is only one block. Yeah. Whereas in a non-star tree, there are more than 1 blocks. So I will just illustrate my algorithm or our algorithm on this tree, and so the remaining part is just going to be some illustration of this algorithm. So am I doing fine time? How much time do I have? 7. Okay. Yeah, in 7 I think I can finish. So here is the tree, and you look at the line graph. So in the line graph, you recall that every edge becomes a vertex, and when are two edges connected, if they have a common vertex. So that's why you have this, and you can check that this triangle is a block because this is a cut vertex. If you remove edge 2, 4, yeah, it will break, so on. So this is a cut vertex, this is a cut vertex, so on. Yeah, you can check. So when you start, of course, the basis is empty, the empty set. So you start with some block, yeah, and then start with a non-cut vertex of the block. So for example, this is the starting vertex, which I abbreviated as SV. So you look at the block. So this is a block B1. So in this block, there has to be at least one other cut vertex. So what do? I take the starting vertex, which is 1, 2, and see, every block is actually a complete graph, right? In the line graph, usually, so there is a characterization of line graphs also. Line graphs has every block is a complete graph. So now you take the symmetric difference of these 1, 2, and 2, 4. You take the symmetric difference, you will get 1, 4. So when you take symmetric difference, I'm going to indicate it by a red edge in the line graph. So this means, so I take 1, 2, and I take 1, 4 in my as a two element subset to form my basis for the row space. So these two will be there in the basis. Then what do? I just delete this block. So when I say delete, I'll first delete the edges. Then the isolated vertices can also be removed. So now whatever was the cut vertex here that I will make as a new starting vertex. So now in this, which is the block, this is the block. So this is my starting vertex. There are two cut vertices. So now I have a choice. I can go to either of them. So if you can go to either of them, so for example, in this thing, I'm going to go here. So I'm going to go here. So this cut vertex. So I will take 2, 4, and because it is here, it is, see, there is more than, if there is another cut vertex, yeah. See, the point is, I am in a block where I have a starting vertex and I have a different cut vertex. Sometimes I may not get a different cut vertex, in which case I will do something different. Yeah. So when I have a cut vertex, I do this, whatever I did earlier. So that's why I get 2, 4, and 2, 8. So now you delete the edges, and now you delete the isolated vertices. So now there are two of them, you remember. So either of them could be a starting vertex. So you start with, so let's say I start with this, and note that this is not a cut vertex because deletion will not increase the number of components in this. So what do? You just add any vertex. Yeah. In this case, any. So in this case, because it's an any vertex, it's not a cut vertex. So I just take 8, 9. I don't take symmetric difference. That's the only point. Yeah. Then of course I will delete those two. Now I start with this starting vertex. You look at this, there is only one cut vertex. So I would have to add 4, 5 and symmetric difference of 4, 5 and 5, 6. So 4, 5 and 5, 6 symmetric difference is 4, 6. So then I will delete that. And then I had 5, 6 and any vertex which is 6, 7. This is okay. So this is the rough idea of how the algorithm proceeds to give a basis for the row space of this max 4-point condition matrix. So there is an algorithm because the sequence in which you do it, where you start with, so whatever your output will be a basis, it's not a unique object. We get a family of bases. The output of the algorithm is a family of bases because there is a choice in where you start from, which if you have several, where you start from, actually that is the important point. And of course, you could do it in some other order also. So you can get any other basis. All outputs of our algorithm will be basis. That's what we prove. So to illustrate, this is the entire basis. Yeah. So we get 2 elements per block of the line graph of T. So the number of blocks in the line graph of T is n minus p. That you can prove by induction, not hard. So since we output 2 elements per block, so the number of elements output is twice n minus p. So for a non-star tree, as I said, star tree is very easy to handle. So number of elements is 2 into n minus p. This is the basis, and you can show the determinant. If you restrict your max 4pc to rows and columns from this output, you would get this to be the determinant. Yeah. Yeah.
Any questions from participants?
So, I would that the past theorem, you know, that was already with the characterization using the distance matrix.
First theorem using, go to theorem 1.
Yes.
Gune once, okay.
Yes. Okay. So it actually excludes that condition that it has no triangles. Right.
No, see, if because this 4-point condition involves 4 points. If you take a triangle which only has 3 points, it still satisfies. So there are
Okay.
having no triangles is just 2. See, this 4-point condition, if you take a tree with n greater than or equal to 4 vertices, you can ignore that.
Is there any other refinement using the distance that exactly?
Yeah, I don't know. See, given a distance matrix, does it arise from trees? That's a very good question. So here is one answer,
Okay.
and I don't see why this is the only way to answer it. Maybe there is another way to answer it. So it's possible. Yeah. I don't know yet, but this is one good way. But I think there would be 1 or 2 more ways. I feel just a gut feeling. I think there should be some other way to answer it rather than this.
Any other questions, please? Anybody?
So there is something using the tight spans, I can tell you. Yeah? It uses some polyhedral, but it's too complicated. That is, you get an algorithm with, let's say, complexity order n to the 4. You check for any 4 points. There it's a much more complicated thing. There is one thing using some tight spans, but it's way more complicated. And from that I'm not able to get anything algebraic. It's some polyhedral thing.
If there are no questions, I thank the speaker for nice illustration and the talk. Very nice, sir. Thank you, sir. Thank you for the nice talk. Now I request Professor S.K. Jain to honor Dr. Sivaramakrishnan just by presenting a shawl.
What am I? Okay. I am supposed to
Yes, sir, that's a shawl.
put it around the shoulders. Yeah. Okay. This is usually done in the Buddhist.
Thank you, sir. Thank you so much.
I'm surprised. Thank you.
That will be great. Okay, that is our video.
Okay. Okay. Yes. Get you back to your lunch. Sorry to bother.
Share screen. Are you letting me share the screen?
Yeah.
1 second.
The next speaker for this today's afternoon session,
Ajit Iqbal Singh. Is it? Oh my goodness.
Professor Ajit Iqbal Singh.
I see.
Please let me.
Yes, ma'am, I have allowed. We have allowed screen share.
Okay.
Yeah.
I welcome Professor Ajit Iqbal Singh, INSA Emeritus Scientist, Delhi, India. Title of talk is Interplay Among Matrices, Polynomials and Quantum Entanglement. Ajit Iqbal Singh is an Indian mathematician specializing in functional analysis and harmonic analysis. Professor Singh is a fellow of Indian National Science Academy, India's apex body of scientists and technologists. She is also a fellow of the National Academy of Sciences, India. Professor Singh began teaching immediately after completing her master's degree as faculty at Indraprastha College, Delhi University. On completing her PhD from Cambridge, she returned to Delhi and joined Hindu College. In 1974, Singh was appointed reader in mathematics at Delhi University South Campus and continued as professor from 1984 to 2008. From 2008, she has been a visiting professor at the Indian Statistical Institute, Delhi Center. Professor Singh has worked on linear operators in locally convex spaces, topological algebra, spectral synthesis in hypergroups, multipliers and module homomorphisms, semi-group algebras, applications of harmonic analysis to differential equations and orthogonal polynomials, geometry of range of vector measure, and quotient rings of algebras of functions and operators. Professor Singh was awarded the Rai Bahadur Brace Mohan Lal Saheb Memorial Gold Medal and Ravi Kant Devi Prize from Delhi University. I welcome you, madam, for this talk.
Thank you very much. Interplay among matrices, polynomials, and quantum entanglement. That's the topic I chose for my talk today. Concrete part. Ever going thanks to the organizers for inviting me here, making me walk down the memory lane, ever so pleasant and dear. Speakers and researchers all over world sphere, discussion with people like Manjunath Prasad, they all spectacular crumbs and good atmosphere. Abstract, I would like to read it because it is very much a part of my talk. You know, the shortest path is the straight line, which is called a vector, and it is started with in a plane. Now let mn be bigger than or equal to 2 be natural numbers, and let xi and eta be vectors of length m and n respectively. The tensor product xi tensor eta can be identified with the m cross n matrix A, which is xi eta t, where t is the transpose. Now this enables us to identify the tensor product Cm tensor Cn with the space of linear space of matrices mmn of complex numbers, and that is size is m cross n, as I said. And vectors like zeta of the form xi tensor eta are called product or separable vectors, and all others are called entangled vectors. Now the latter, they correspond to matrices of rank bigger than or equal to 2. Even Shiva Ramakrishnan was talking of rank of matrices. They are relevant to us. Now, quantum entanglement is an important and useful concept in quantum information theory because entangled vectors cannot be figured out by one party only. You need two-party information, whereas separable vectors can be, guessed by taking partial traces on one side and then the operator. And maximally entangled vectors are those for which partial trace is the identity operator, and they correspond to unitary matrices. So for multipartite setup, we take tensor product of Hj with Hj Cdj, dj bigger than or equal to 2 for each j, 1 less than or equal to j less than or equal to k. Now the nice thing is that they can be identified with polynomials of with complex scalars, and in k variables x, xj, j varying from 1 to k, and with degree in xj less than or equal to dj minus 1 for each j from 1 to k. Now the thing is that physicists like to one rather than 1 to up to dj minus 1. And they have different notation also. Their inner product is linear in the second variable, and antilinear in the first variable because of Dirac's notation, which is easy because we take this kind of formation. Now this is there, and a space which is completely entangled in the sense that the only non-zero vector are, all the non-zero vectors are entangled. So 0 is the only product vector. And we usually denote this by script S in this talk. And there are essentially two ways, starting from basics. One is coming from unextendable product basis. And unextendable product basis is a set of vectors which are mutually orthogonal. And there is no orthogonal vector in the space which is orthogonal to these. And if I take orthogonal complement of this unextendable product basis, that will become a completely entangled space. Another method was given by K.R. Parthasarathi concretely. You see, Parthasarathi gives concrete things. The results may be guessed, may be known by people, but Parthasarathi will come with full proofs, full concrete formations. And that was given by Parthasarathi, and he will give it in full generality. UPBs were given for certain dimensions and methods for other dimensions too. And stalwarts have worked in UPBs. And now, if you take Parthasarathis method, he takes product vectors and he uses 1D matrices to take n+1 orthogonal vector, or n+1 vectors, orthogonal or not, and takes their orthogonal complement, and that is completely entangled. And so the contrast is that for UPBs, usually the linear span contains only finitely many product vectors, but for Parthasarathi space, the space contains infinitely many product vectors, and its orthogonal complement is the completely entangled space constructed by K.R. Parthasarathi. There are, now recently, we noted some contrasts that UPBs, the span may contain more product vectors. And if you join a member of UPB with the orthogonal complement, that may still contain product vectors, even though the original completely entangled space contained no non-zero product vectors. Now, if you combine 2 from UPB, then there are infinitely many product vectors. Now, similarly for Parthasarathi space, if I take one product vector from the space U and combine it with a completely entangled space, there may be one or no more product vectors. But if I take 2, there will be infinitely many. So all these things are collected in a joint paper with Ritabrata Sen Gupta from IISER Berhampur. Paper is typed, but typos are being corrected, and I'll let you have a glimpse of the paper towards the end of the talk. And I dedicate this talk to in fond memory of my inspiring revered teacher, K.R. Parthasarathi, from whom I learned a lot, particularly fundamentals and advanced topics in quantum information theory. Now, this is Som Shubhro Bandyopadhyay, is a physicist. I have worked with him and published this paper in Contemporary AMS Maths. And this is, you see, there is, he's explaining quantum entanglement, its role and its importance. So I will let you read it rather than I read it. Now, you see, I do not know tech, so I copy and paste and, cut and paste. And then I prepare my PPT. So reference numbers come and some other things, extraneous things may also come. But reference numbers, these are reference numbers. And in the appendix of my talk, I have collected all these references also. They amount to, more than 10 pages. Now, this is resonating valence bond state. We take a set of size, even size, and then divide it into 2 equal sets, A and B. Here A is in red color and B is in green, even though it says blue in the caption, And then we let points of A go to points of B in one way. And it is, you see, this point in A goes to B, and this point in A goes to B. They are adjoined like this, you see. This point in A goes to B. And now the example that I have given is of nearest neighbor covering. It is called a covering, where we can only move on the right or left or down. Arrangement is with this nice thing in mind, that nearest neighbor is a pictorial nearest neighbor. And so it is nearest neighbor. Even A is going to be neighbor B. This is going to as a neighbor, nearest neighbor. Now what we do is we take A and phi A, corresponding member of B, and then we take qubits, that means 0 and 1 are the two basic vectors, and we make 0 sit at A and 1 sit at B. That is, A position is first position, B position is second position. So 0 sit at A and 1 sit at B, and then minus 1 sit at A and 0 sit at phi, which is B I was calling. And then divided by √2 to make it unit vector. This is called a singlet. Now I take all vary over points of A and then multiply means tensor product. Multiply all these singlets. And so I get, new pairs sort of, tensor multiplied. So I have divided the whole tensor product into two things. And now this is corresponding to that covering. Then I vary over coverings and sum over coverings and normalize the vector. That is called a resonating valence bond state. And entanglement of resonating valence bond states is taking very easy form through polynomial representation. And the Nobel laureate in 1977, Philip Anderson, and this is his centenary year, and 13th December is his birth centenary, and he died at in 2020, at age of 97. So if we do good mathematics or physics, we will live very long. And he made fundamental, significant contributions to resonating valence bond states, particularly doped bond states, where singlet type of interaction or resonation does not take place in some pairs. That means only spin up 0, 0, 0, the vector for a dope, for a hole also, it is called a hole or a dope, that will be just sitting as 0, 0 in that product, instead of singlet 0, 1, minus 1, 0 divided by √2. And as I have already said and written in this paragraph, nearest neighbor, resonating valence bond states, periodic nearest neighbor, where I allow the first pair also join hands with the last pair. And that is called periodic, like Fourier series, 0, we will let the first thing join hands with the in-between thing coming from period. So periodic NN watts and doped periodic nearest neighbor resonating valence bond states, they are all genuinely entangled. What is genuinely entangled? If you have a multipartite setup, which we have for resonating valence bond states, if you divide the index set in any two parts, that is called bipartite cut, non-empty this way and non-empty complement, and then it is entangled in that bipartite cut. So in every bipartite cut, it is entangled. It is called genuinely entangled. All these three things are genuinely entangled, and proof is very easy from polynomial representation, which I will show you if the time permits. Now, zeros of multivariate polynomials and factorization. What is more important are prevalent. Now, we've all learned to factorize a polynomial when we were in higher classes at school, and then identifying one with 1 and x sub j with spin up and spin down. Spin up is 0, spin down is 1. And then this will create for entanglement a quick good tool, and take higher powers for variables too, for higher dimensions as a rule. And basics in algebra, analysis and geometry of polynomials fill with the endless string your application spool. Now, stable polynomials. What are stable polynomials? Single variable or multivariable polynomials. They are called stable if they have no zero in the upper half plane parts. That is z, imaginary zj bigger than 0. There are no zeros there. Polynomial is called stable. And here is, strictly stable if this is allowed to be imaginary z bigger than or equal to 0. And there is lot of developed theory and given in these references. And then if I take, this is for, I have already said this, so I go to the next slide. And people will like this theorem, which I am stating, and I have proof written if anybody wants it. And this is, let A1 AN, A1 A2 AN be positive semi-definite matrices and A be Hermitian matrix, and consider this polynomial, which is determinant of this matrix sum, A0 plus x1 A1 up to xn AN. It is either stable or identically 0. Okay, and we can check all these things through diagonal matrices. And now, as I said, that polynomial representation makes our job easier to determine the entanglement or separability. And I have already told you about Somshubro and I writing a paper, and I gave several talks in conferences in India and abroad, and American Math Society conferences and workshops, and Nottingham and Memphis and other places, IIT Guwahati, various places. And then this paper, I went to visit Calcutta, and Somshubro and I sat down and wrote this paper, and then we corresponded with emails. And Talmor was visiting there. He's one of those 6 who revived quantum entanglement with Joza and Bennett and so on. Now we could discuss those things, and this is the paper I have already shown you, and this is the abstract, and I will give the contents also in a short while. So then this was followed by another paper, the polynomial representation of resonating valence bond states. And this is with Aditi Sen and Ujjwal Sen. I visited Allahabad several times, Prayagraj I should say. And I would, whenever I went for a meeting of National Academy of Sciences India or otherwise, I would spend some time in HRI, sometime in week or more or less. And then this paper was developed, and it is on archive, number is there. And I have already given you idea. And here is the polynomial representation. Now it may look like a mathematical jargon, but when I speak, I hope it will not look like that. You see, we have dimensions dj for hj. So basic members are written from 0, 1 up to dj minus 1, sitting at jth factor. And so tensor product will be given by basis, and basis, a member of basis corresponds to a tuple, k tuple, I1, I2, Ik, where ij varies from 0 to dj minus 1. And this I, this is this, as I varies over the set of these tuples, then that will give me a basis, and that is the easiest possible representation of tensor product. And what will be the product vectors and what will be entangled vectors? That will be sigma ai and I. I is the product vector, tensor. And usually in physics, they will forget the tensor symbol, and they will just write the basic number next to each other. And then it is called product vector if it is of the form xi tensor eta, I said. And for this multipartite setup, xi1, xi2, xik, and then all tensors, this will be product vector, all others will be entangled vectors. And I remember I told you they correspond to matrices, but for multipartite setup, they won't correspond to matrices, but polynomials help us to study them. And how do I represent polynomial to multiple, to n tuple, k tuple index I make correspond the polynomial, monomial, x1 raised to I1, x1, x2 raised to I2 up to xk raised to Ik. So they become basic members. And where do they become basic members? They become basic members in the Hilbert space, which is the tensor product, and they become orthogonal. And it is L2T of the L2 of the unit circle, because in unit circle, this will be orthogonals. If I is not I dash, then vector I or polynomial x raised to I, as I explained to you, vector x type raised to I, they will be orthogonal. And for partition E, if we can see E entanglement, if I take a partition, and bipartite cut is only partition into 2. And so we have this. And now I come to the next slide. And here are some examples down. So this is, and all these are vectors in tensor product. Some are entangled, some are not entangled, and it will be very easy to see when I look at the product at the polynomial representation in a short while. So polynomial representation, I have already explained this to you, so I won't spend too much time on this here. And here is this thing that I have already explained this L to T. And here are the polynomial representations of the vectors that I told you. Now, the polynomial representation is 1 plus xy. So when will it be a separable or product vector? If it is product of two polynomials and the polynomial domains, variables are separated. So if there are less number, then I write xy or xyz. So it is 1 plus x into 1 plus xy, which is not separable. It is not a product. Single degree is not a product. But when I take, here there is a product, here there is no product. So I can simply figure out from trying to factor a polynomial. And here is, I already gave you poem, factorization gives me this thing. Now, some examples of entangled vectors, and they are for one-Darmon determinants. So everybody knows one-Darmon determinants, not only knows, perhaps everybody likes them too. So this is 1 x1 square, x1 is to n1 minus 1. And this is, here I have changed the domain from k to n because I took this from another paper. And this is, you see, 1 x1 goes up to 1 x2 square. And then this is xn raised to n minus 1. Everybody knows that the value of the determinant is this product, xj minus xi, I less than j, and I varying from 1 to n, j varying from 1 to n. And then it is not separable because I cannot separate variables. If I take x1, x2 comes running, x3 comes running. If I take x2, then x4 also comes running. So I'm not able to express it as a separated product. So it is entangled. Actually, it is generally entangled. No bipartite cut will be available. And you can construct more from this, which I will not dwell time upon. Now, binomial polynomials. Consider x plus y raised to n. So, or just say x plus y itself. X plus y square is x square. Separate the variables because x plus y raised to 2, then each one is homogeneous, and so this binomial representation is an entangled vector. And now this is, I have written this, but the nice thing is that if I take orthogonal polynomial systems, most of them satisfy this binomial relation. Pn x plus y is NCR and PRX and Pn minus Ry, and R is varying from 0 to M. So all these will be entangled vectors. And how Ajay Shukla told me, I went to a conference, attended a lecture by Ajay Shukla that was at Jamia, and that was at MIT University, and then another one at Jamia. And then I said, we are discussing this, and he said, oh, they cannot be, separable, because if I take this is a Laguerre polynomial ln x plus y, it is expressible as binomial for Laguerre's polynomials coming from related classes. Now, if this is px qy, then px has zeros, qy has zeros, but left-hand side has zeros coming from x plus y equal to ak, and that is a line kind of thing, or one-dimensional subspace. And right-hand side is first 0 for x, and then the whole space for the second one. So the two things are not possible, and therefore it is entangled. So I have already given you proof, and I have already given you binomial rule for this. And there are at least, in another talk at Memphis, I gave 12 references for binomial polynomials. Now I won't give. Now you take any complex polynomial and treat it as variables x and y. X and y are real part. So my tensor product is in terms of xy, but my polynomial is in terms of z equal to x plus iy. It is entangled, and I have given 3 proofs. I will just tell you the first one, because there is Cauchy-Riemann equation type, and Cauchy-Riemann equation type, it reduces the degree, that differentiation with respect to x reduces the degree in x, and differentiation with respect to y reduces the degree in y, so the two sides cannot be equal, and therefore, px, it cannot be expressed in terms of pxqy. Here is another proof. Here is that Cauchy-Riemann equation proof. And in the previous slide, I had given you how to deal with many variables. Construct from several complex polynomials and multipartite setup and tangled vectors. So this is, I have given these 3 proofs. Now, Bell polynomials, many people here are doing statistics, and many people are doing models and combinatorics. So Bell polynomials are related to combinatorics, to partitions. To partition the number, and also you take JLJ, and this is the partition. The two sets are equal because one is partitioning and restricting the sum, and the other one is giving smaller size tuples. This one is giving larger size tuple with conditions. And now the Bell polynomial is constructed like this, coming from this partition. Now, next page gives the properties of Bell polynomials, and then tells us that Bell polynomials are also genuinely entangled in several variables. But as you see, the number of variables increases with n, and therefore the degree and number are related, and we can have different polynomials. So you got several examples. Now, resonating valence bond states, I have already explained this, how we divide this in 2 parts here, dots and dots within circles rather than colors. And there are many examples. Our paper on archive has various pictures, various examples, and I can index A by odd numbers, B by even numbers, and then it becomes a permutation from 1 to new to 1 to new, and set of permutations has Fibonacci number as its number. So I have already explained this, but now it is the polynomial representation. So 0 at A and 1 at B, and 1 at A and 0 at B. And so it is this tensor product, and its polynomial representation is here. It's here, as I'm showing you in 3.3. So then we take products and we divide by root 2. So this product will be, multiplying by 2 raised to minus n by 2, and all these factors will be put together. But they are not entangled, because 2 by 2, they are not genuinely entangled. They are entangled, but not genuinely entangled per covering. But if I take too many coverings and then I add them, I have written the polynomial representation of this for single covering. At single covering, note this factor x raised to A and x raised to B, and this is what it is, which is important, and it helps us to prove entanglement. So if I take a subset of A and then a corresponding image of that subset from B, I have to remove that part, and then I take the products from variables coming from B. Degrees are less than or equal to 1. So either xj is there or it is not there. Not there means 0 vector. Is there means 1 vector. And so this is now I have taken, when I open it out, this is the representation 3.5. Now I take a set of coverings and 2 coverings at least, and then I add them and normalize later, and this is the representation. So it's too clumsy or too complicated to see, and one can see the papers. Okay, but now if it is a product vector, then this is the condition that must be satisfied, 3.7 for psi. And for all psi's, this should be satisfied, that if it is product vector in bipartite cut E dash, then it has to be, like this. So here is the proof for this that I explained, and here is the proof, and here is polynomial representation of RVB states, and that is now doped state. Doped, I already explained that 0, 0 only will sit. So for gaps, I will be collecting the powers xj from B's by removing the gap. So this is that the doped state is generally entangled, and here is the proof, and I will not give it. And now this paper is in the proceedings of the earlier Iclaa, and there we gave partial transpose, and somebody gave partial transpose earlier also. And this is here is the naive approach. And every map from matrices to matrices can be given by a bigger matrix where image of EJK sits at jkth place as a block. So here are elementary matrices, blocks, 4 of them. Partial transpose of each one gives me this, and it is called partial transpose. This is positive definite, but this is not positive definite, semi-positive definite, even not that. So what it is that transpose spoils when the things interact with the environment. That is, the transpose is not a completely positive map, even though it takes a positive semi-definite matrix to one of the same kind. And we say partial transpose does not take positive matrices to positive matrices. So separability, all this was separable states. Now mixed states, I take one positive matrix, another positive matrix, tensor them and take the sum. This is called a separable state, and otherwise it will be, entangled state. Okay, 7 minutes, yes. So this is that the decompositions are misleading. Spectral decomposition may mislead, because the state may be separable in terms of non-orthogonal product vectors, but it will not be separable in terms of orthogonal vectors. And this is completely entangled spaces. I already gave the idea. And this is unextendable product basis by stalwarts. All the stalwarts are there. People who work in entanglement know these names by heart. And this is, that one advantage is that completely entangled space coming from UPB has projection as positive under partial transpose. Now, these are one example of UPB in 3 tensor 3 setup, and then another example in 2 cross 2 cross 2 setup. We call them 3 qubits. And I gave polynomial representation also. And K.R. Parthasarathi gave maximal dimension completely entangled space coming from these and their products, and then from products collect this number that will be linearly independent by one Diermont matrix. Orthogonal complement will contain no product vector. Now recently Talmor and Boyer, they studied where I can add some product vectors to completely entangled spaces. I can allow them. And then the separable states are completely specified. So even they are useful. So this was for smaller dimensions. And then recently on arXiv, Talmor and Rotem Liss, Talmor student, and Andreas Winter have this paper where they take higher dimensions, but mostly dimension 3 subspaces. And here is Ritabratan Sengupta and myself. We have written this paper. It is typed, only typos are being corrected. And as I said, I will let you have a look. What we noted was that if you take span of UPBs, it may contain more product vectors. And if you adjoin one member from UPB to the orthogonal complement, it may contain product vectors, only finitely many. But if you combine it with 2, then infinitely many. And then we looked at KRP space, K.R. Parthasarathi space, and we found that the situation is different. If you take combine one with this thing, there may not be too many. That single one only will be there, and computations are pretty long. And then I thank you for your kind attention. And I will now, these are the references, and I show you, I let you have a glimpse of. Yes, so this is the paper. I can only let you have glimpse because it's a long paper, and typos being corrected. So here is this paper. Only a glimpse, only a glimpse, only a glimpse, 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 glimpse. You see, we have to take this thing. Okay, only a glimpse. And UPBs are being worked out even now. And here is this recent paper by Pritabrata was postdoctoral fellow when I was at ISI. I left ISI in November 2014. I have to correct the person who introduced me. And then he is working as PDF of Pritabrata, So he's my grand postdoctoral fellow, and that is UPB recent paper. I showed you that. Yes. Fine then. So this is Haldar. Haldar is his name. Haldar, and this paper is another one because co-authorship is not a transitive relation. It is a symmetric relation. So this is co-authored with somebody else. Pavneet? वही चला गया सब कुछ कहाँ चला गया अच्छा अब मेरा फोटो फुटे ही आ जाए फिर क्योंकि वो क्वेश्चंस पूछेंगे yes I am back I'm back अब
very comprehensive.
Thank you very much. You are my source of encouragement. And continuous one, not only discrete.
Thank you, madam. Any questions from participants?
Is there anything in chat?
I'm glad. Okay, I'm very glad that I came at the right time to hear your lecture. Hello.
Thank you.
Can you
Hello?
hear me? Yeah, can you hear me? Hello.
Yes.
Can you hear me?
Yes, I can hear you.
Okay, I'm glad I said I'm here. I just walked in about half an hour ago.
Okay.
So I'm so pleased to hear you as always. You're full of enthusiasm. My God, I cannot even believe it that you have told us so many things which,
Thank you.
in one breath. In one breath.
And I'm lucky that you are here. I'm lucky.
Yeah.
Luck is mine.
I wish you were here also, but I had to go to China first, and then we could not come together.
Yes.
Anyway,
Good.
I'm glad that I heard it. And I congratulate you on all your
Thank you.
work. And
Thank
best
you.
wishes.
Thank you very much. Thank you. Thank you, Manjunath, again. And your team, your very active team. And I am learning a lot from your wonderful conference.
Any other questions, please, participants, delegates? If there are no questions, thank you, madam. Very nice lecture. Wonderful. Thank you once again.
Thank you. Most welcome. Thanks for your attention. Thank you.
Thank you, Professor. I would like to thank Dr. Kuncham Shamprasad, sir, for chairing the session. Thank you, sir. So this is the end of day 2. I request all of you who are participating in the cultural evening to gather downstairs. We'll leave soon. Thank you. Tomorrow's session will start morning 9 o'clock.
Yeah. I will walk like today. The morning walk is good. I saw okay.
अभी है ना वो भी है.
You please get the kit, sir. He has the kit. Some towel and water bottle and all of that. He will give. Caretaker will give. He is there. Yeah. Okay. Yeah. Okay. Yeah. Okay.
What's up? I come back here, no? How when are we?
We are not coming.
No.
Yeah.
No. How when are we?
अरे कहाँ पे?
By bus. No, itself. Buses must have arrived.
No, 23 बस फटक भाई. I didn't get that.
अरे वो कैसे लीव करनी है?
Okay, no, she's asking something. No, I think she doesn't. Then you
Uh,
can come
uh,
by, come by bike. End the meeting. No, no. End the meeting. Island.
Yeah.